Go ahead, please. Viru, project your
Yeah,
the PPT. Share your PPT.
can I visible, right? The display is visible, right, everyone?
No, no, no. You have to share your PPT.
Do you need some help, sir?
No, no, no. One second.
Yeah, it's visible, sir.
Everyone visible, right?
Yes, sir. You can make it full
Yeah,
screen, sir,
okay.
in slideshow mode.
Yeah, I will do it.
Thank
I
you,
will
sir.
do it. I will do it. Yeah, today we are going to look at on the FPGA introduction about FPGAs. So today we will start with introduction about FPGAs and what is FPGAs and how to use and what is applications of FPGAs and all. So today first we will look at on the RTL design flow. Next what is FPGA and what is FPGA architecture, the RTL coding and what are the RTL coding styles and difference between SOC, ASCII and FPGAs. And then finally, we can discuss about any questions regarding FPGAs and SOC or any coding and also. So you can look at on this today. First, we look at an RTL design flow. So RTL is nothing but a resistor transistor level, right? So in this design, so FPGAs, how will fabricate, so what are the designs flow you have to look at on this once you start with the RTL means first you will do the specifications, means what are the specifications you do, what do you do with an FPGAs, first you understand the specifications from the customers. As you talk about the industry level means first you understand the specifications. So after that you go into the design entry. So design entry is nothing but a FPGA coding. So it may be very long VHDL or schematics. So you can write your codes in using the very long VHDL. And also you can, if you are an expert or if you have a good knowledge in the digital design means, so if by using the schematic diagrams also you can do your design entry. From the schematic you can convert it in a VHDL or very long. Then you can synthesize the simulations, you can do it also. So design entry have a three or four types. You can use Varilla coding or VHDL coding, and nowadays we are system Varilla and schematic, and also you can use custom IP from the tools. So if you are using a Vivodo and ISC, Xilinx ISC or Quadras, so you will get some default customized IP from the tools. Is it from like SPI, UART, Ethernet, and the DR3 and PCI? All these are the coming in IP. So from that also you can use your design. From that you can convert into your simulations. Once the design entry is completed, next you are going to the synthesizing. So synthesizing means you will convert our design or code into a net level list. So it means that it will convert our code into a logical design level. It's called an NCD flow. So it will get in the .NCD format. So it has a number of NAND gate and NOR gate and mux and divide. So it means that it will convert our design into a logical gates ways. So once the simulation is done, you will go to the mapping and placing and routing. So what actually means placing and routing means, so you're making the proper place and routing to the FPGAs. Why it is means to make the optimizations and to make the proper connections between the uh, gates. Okay, so mapping and placing, and it is mapping and placing route will comes in the implementation. I will explain it later. Then once the synthesizing is done and mapping and placing and translate is done, then you will go into the program. So before programming to the FPGAs, you convert into a bit file. So this is a simple and RTL design engineer level of flow chart. Using there are mainly four levels they are looking. One is the design entry, another one is the synthesizing, another one is placing and routing and programming. So in any FPGA fabrications, any FPGA users, there are more three main role engineers will come into picture. One is RTL design engineer, another is PD engineers. PD engineers are nothing but physical design engineers. Another one is verification engineers. So difference between these three engineers to fabricate any FPGAs, users of any FPGAs means the RTL design engineers main role is writing the codes, synthesizing the codes and making the placing and routing and timing analysis, and they are making a fuse to the FPGA. So, and PD means physical design engineers. So they have some of the more tasks in the FPGA applications and users. So it means that, so as I told earlier, first we look at the system specifications, what actually we are going to do it. Once you understood the our specifications, you'll go to the architectural design. So architectural designs is nothing but schematic diagram wise. So schematic diagram wise, and they can use for the VHDL Varila coding also. So here small one is the entity port declarations and end entity. So in the entity wise, you declare the ports, input output ports. Okay. Then functional design and logic designs. So you will go into the do the our functional operations. What is actually we are doing the what functions you are using in the designs and logical designs. So if you are in the using the circuit diagram, also you can do it by the NAND gate, OR gate, or any gates. You can do the circuit designs. Then here main role is physical engineers. Is it? They were partition, floor planning, placement, clock tree synthesizing, signal routing, timing closure. So physical engineer, design engineers, they have to do the partitions of the all the gates and floor planning of the FPGA IC, and placement with proper placement that they have to do with the uh, before the fabrication to the any IC, and they have to look at the clocking also. So very important in FPGAs and any SOCs is the clocking frequency. How much frequency you have to use, and what is it getting the proper time delay or proper timing with the FPGAs also you have to very important. Signal routing also is very important. Timing closure. So these are the main roles of physical design engineers roles: partition, floor planning, placement, clock tree synthesizing, signal routing, and timing closures. Then physical verification and sign off, and layout post processing, fabrication, packing, and testing. So one FPGA has to make means you have to do the all these steps. First is system specification, architectural designs, and functional design and logical designs. So these are comes in the as it here design entry. So specific, once you know the specifications, so you will go to the design entry. In the design entry, architectural design, functional design, and logical designs will come. So after this design entry, will go to the synthesizing. In the synthesizing, you will do the circuit design and physical designs. Then you will go to the placing and mapping is nothing but the physical verification and sign up, layout, post processing, and fabrication. Since fabrication and packing is nothing but the manufacturing of our FPGAs. After this also you are going to the manufacturing. So this comes in the validation engineers, means verification engineers and validation engineers. Okay, so these are the three main role engineers, and this is the very important. Your interview question also a very important question. This one, what is RTL design flow? Also very first question and very important question also in the interviews. What is RTL FPGA design flow? Also understood, right? Hello, can you hear me?
Sir.
Sir, yes, sir, you are audible, sir. Carry on, please.
Yeah, okay, understood, right?
Yes, sir.
So in the program, so you can do the programming by using the PRAM, EPRAM, downloading and programming. It means that so it convert our BRAM, our code into a netlist, and the after netlist we will converting in a programmable format file. It may be in a SRAM or flash RAM. So SRAM is nothing but storing in the memory. The SRAM you are storing in the memory. The flash means you are storing in the NAT flash. Okay, by using the different cables, programming cables, it may be serial programming or parallel programming, and based on your tool also you have to use specific cabling and tools to download to the FPGAs. Okay, so it can be .x file or .bin file or .bit format, .ecr format. So all these formats will go. You can do download the FPGA. Okay. So actually, what is mean by FPGA? First, you understand what is mean by FPGA. I think everyone knows it. So FPGA is nothing but a fate programmable gate array. So it is in a semiconductor device, or you can call it as an integrated circuit IC. This is mainly used for digital logic designs. So FPGA is used for the digital logic designs. Means once you know the digital logic designs means so AND gate, making the AND gate and OR gate, NAND gate, and max combinations and sequential circuits. You know all this comes in digital logic designs. Okay, so FPGAs can be reprogrammed to desired applications or functionality requirements after manufacturing or fabrications. So main advantages and why FPGAs is used means we can reprogram number of times with your desired applications or functions requirement after manufacturing. After manufacturing FPGA, you can do that. So this is a very important difference between ASCII and FPGAs. So one first you will do the fabrication of FPGAs. After that, we can program your desired applications or functionality as per your requirements, and also you can make it number of times. Understood, right? So reprogrammed is nothing but you can program, you can dump your design in FPGA IC number of times. You can erase and you can download freshly and you can reprogram and you can override to the your desired applications. Okay, so this is the main important mm, mm, advantages of FPGAs rather than other ICs. So what are the applications where actual FPGAs use it? So nowadays in everywhere FPGAs are using, like in communications and medical, aerospace and defense, image processing, and image processing, video processing, data centers, data, data center and automotive. So applications of FPGAs is nothing but they are using applications of FPGAs is so communications wise means in the telecommunications also nowadays FPGAs are using, and in the medical field also you are using FPGAs. So and aerospace and defense and image processing and video processing and data centers and automotives. The telecommunications is nothing but to making the nowadays all Intel and other big companies are using the 5G all the technology using FPGAs only. So because of I told you, you can use a number of times, you can reinforce the our designs in number of times. And once FPGA is fabricated, based on your requirement also, you can fabricate the FPGAs. How many is you need some of the chips in 256 pins and number of LUTs and number of D flip-flop, number of DSPs also you can make it by the fabrication. After fabrication, you can fuse your uh, design. So in the telecommunications also our FPGAs is using on medical. So nowadays in all the medical equipments like X-rays and operational equipments are coming in by using the FPGAs also, and aerospace and defense. Even defense also nowadays they're making their communications. But communications also they are using in aerospace also the FPGAs also are using. Even email processing, video processing nowadays all the projects. In academic as well as commercial companies are using image processing and video processing projects in using FPGAs only. You know, CNN algorithms and AL and A and ML, all algorithms also you can dump to our FPGAs also by using Python and C and Verilog also you can make it for image processing and video processing applications, right? And data centers. So data centers means to store our big data. You know, for that also you can use the number of RAM size and instead of all the fabricated in FPGA. So you can use data centers and automotives. So all the automotive vehicles and also coming in the smart automotive vehicles and coming in using FPGAs only nowadays. Okay, so these are the FPGAs. And why actually FPGAs are using means it is because of its low power consumption and low cost and reprogramming and flexibility and scalability are also very good in compared to other fabrication ICs. So these are the FPGAs applications and why FPGAs are using. Okay. So this is an FPGA architecture. So any FPGAs is in a basic and common architecture FPGAs. You can take it as a lattice FPGAs, Xilinx FPGAs, and some quite difference in Alter FPGAs. Alter, and so now it is in Intel FPGAs. But yes, almost FPGAs architecture is similar and basic. So this is a very important questions in the interviews also and examinations also. What is FPGA architecture also? So actually FPGA architecture. Sorry.
Hello, ma'am.
Yeah, tell me.
Sorry, sir. Please continue.
Okay. So FPGA architecture is consists of mainly three blocks. One is interconnect wires and configurable logic blocks and I/O banks and switching matrix. So there very important is I/O bank, switch matrix, and configurable logic blocks. So you can see here, so then three lines is coming right. It is an interconnect wires between the two CLBs. Between the CLBs, it will connect the wires. It's nothing but a wires interconnecting with the CLBs. So each CLBs have a LUTs. LUTs means lookup tables. Each CLBs, please understand this one. Configurable logic blocks is consists of LUTs. Each LUTs consists of D flip flop, adders, and mux. Make it an LUTs. Understood, right? So configurable logic blocks is consists of LUTs, and each LUTs consists of D flip flop, adder, and mux. Okay, and switching matrix. So this switching matrix will design our it will route the our design to the respective CLBs and IO box. So IO box is nothing but input output pins. It is an external connections to the FPGAs. It is a squared FPGAs, right? So you have a input and output pins to external work connections, input and output blocks, and also you have a ground and uh, low voltage configurations also, and these are the interconnections between the CLBs. This interconnection these between two CLBs, right? So as I told, FPGA mainly consists of three blocks. One is interconnect wires, CLB, and IO pads or IO banks. So interconnection wires between the CLBs, and each CLB consists of LUTs. Number of LUTs as a adders, flip flop, D flip flop, and mux. So mux is very important, and the adder also very important in our FPGAs. What are the where design is coming and it will convert in mainly in mux and adders and D flip flop. Okay, and IO ports. These IO ports also means input output pins to the FPGAs to connect external devices like microcontroller, processor, and any other your application, business applications. You can connect input output pins. Okay. So nowadays you can see the SOCs also, FPGAs also, and ASCII also. So what is mainly difference these two between? And all these are using for the logical designs also only. And what is the difference between SOCs and FPGAs and ASCII? So you can see here, so SOC is a FPGA and also ARM processors. So ARM processor plus Altera means is an FPGA. So is nothing but SOC. SOC is nothing but system on chip. So system on chip means so it is this chip is so I am looking, so you can see here Altera SOC FPGA, right? So this consists of a ARM processor system as well as Altera FPGA. Not only Altera, any FPGA, any SOC, it may be Xilinx SOC or Lattice or Macro Semi or Macro Chip. What are the SOC? So just I am giving example here. Altera, I took Altera SOC example here. So here ARM processor is there and also Altera FPGA. So FPGA is on 28 nanometer FPGA and Cyclone 5 FPGA. So Cyclone 5 FPGA, I think you may know Cyclone 3, Cyclone 4 and Cyclone 5 FPGAs also there. So this SOC is consists of ARM processor as well as Cyclone 5 FPGA called SOC. It mainly means it has a processor as well as FPGA. It's called SOC. Okay, and FPGA means as I told now, it is a field program gate array, and ASCII. ASCII means application specific integrated chip. First, it will do the designs. Based on a design, you will manufacture the IC integrated chip or device. So ASCII and FPGA difference is In ASCII, you will do the design first. Based on your design, you will fabricate the or manufacture the chip. Example is your microphones, earphones, right? So, and it is only specifically one applications you can use. So, ASCII is nothing but you can use it for the only one applications, right? So, your microphones you can use for any other applications? No, right? So, if it is used for only hearing your music to enjoy, isn't it? Earphones also, right? So, they have very specific applications, right? Microphones, earphones, and other any commercial the applications will come, right? So these are only the specific applications. When calci also, so calci also you can can see. So these are comes in application only specific applications also you can use rather than other than applications you cannot use. So for that you will do the first design, then you will based on the design. So based on your design size, you will trigger the or you can manufacture the ASCII chip. Understood, right? So SOC is system on chip. So it's nothing but so example you can give SOC means your digital camera. So in the digital camera we have some small processor as well as FPGAs. Okay, and your computers and laptops and your mobile phones also they have some processor and as well as FPGA chip. Okay, so FPGAs. So for India, there are mainly three vendors supplying to India. Overall, India only three suppliers mainly for all industries. So one is Xilinx FPGAs, Altair FPGAs, and Lattice Diamond FPGAs. Microsemi, microchips are coming for the academic wise and small FPGAs, and but in the industrial level and for all applications wise and all the suitable is Xilinx and Altera from the earlier also and nowadays also the idling called Alter is very famous in India vendors and other countries are they're using some other FPGAs. But India the mainly three vendors so Xilinx, Altera and Lattice Diamond. So Xilinx and Altera some little lookup table I told lookup table some small difference is there and Lattice and Xilinx same can use for the based on applications. Based on applications, how you are using the FPGAs, how you select your FPGAs means we can use any vendors. So some of the very familiar with Xilinx FPGAs, some engineers will be familiar with Altera FPGAs and lattice diamond apple also. So based on your requirements, how what is the actually main requirements means your application means size of your designs and budget means cost of our means so compared to Xilinx, Alter is very costly. Alter FPGAs is very costly and lattice diamond also little bit cheaper than these two Xilinx and Altera. Based on this, your cost and power consumptions and flexibility and your design and utilizations, you can select your these applications. And some size of the lattice diamond is small compared to Xilinx and Altera, and low power consumptions and reliability and utilizations. Altera and Xilinx is both are same, but little costly. Altera FPGAs is other than Xilinx and lattice diamond. Okay. So as I told RTL design, so actually how we will do the RTL design engineers. So you can use the combination logic designs, capture we are using equations or truth tables means K map and canal map comes. So from that also you can design your RTL design and convert to circuit and sequence logic designs also we can make it and using the FSM. So finite state machines also from the FSM also you can design your RTL design. The RTL design is method of creating a custom processor also. As I told, you have inbuilt IPA also there in the based on your tools. Tools from that also you can do the RTL designs. So as I told, so you have a 1 second. I will forget one thing. As I told, so in Altera FPGAs, if you're using Altera FPGAs, you have to use a Quartus tool. So based on your FPGAs, you have to use the specific tools. So then only you can do the fuse to the download to the FPGAs. So if you are using a Xilinx FPGAs, you cannot use the Quartus FPGAs. For the coding wise, for the specific synthesizing wise, you can use any tool. but you are using the FPGAs, you have to download your design to the FPGAs. You have to do the particular hardware model means, so you have to use particular tool and design also. So I am using the Xilinx FPGA board means you have to use for Xilinx ISC or Viewer tool to download to the FPGAs. Okay, so if you are using Altera, you are using Xilinx ISC tool means you cannot do it. In the Linux you can do it, but if you are using Windows means it's difficult. It's not difficult. It's not be possible also. Understood that if you are using the hardware as a Xilinx means you have to use the Vivoda or ISC. Okay, and Altera means you have to use the Quartus tool only. Then you can download to the FPGAs. For the designing wise, for the checking your designs or for checking your synthesizing and making the timing and all, you can do it by any tool. But for downloading to the FPGAs means you have to use the specific tool to the board and specific programming cable also. So if you're using Xilinx means you have to use, which one is JTAG you have to use. JTAG, you know, then Janking test access group of that cable is coming from 20 pin cable connector is there. No? From that also you can do it. And nowadays all the FPGAs coming in the USB port only. From that also you can use it. But mainly in Xilinx ISC or Vivoda tools are using JTAG connector. If you're using Altera means you have to use USB blaster. Okay. So USB blaster also you have to use. That is also they have a different to connector, and that is the lattice the blaster is same. It is as a USB quarters connector. It will come. It will okay. So let's continue here. So RTL designs, you can use the combinational and sequential logic designs, and you can making the if you have a truth table or equations also means DFTs from the DSP applications. Signal processing applications, you can use a truth table and equations also you can using and converting circuits. As I told you, if you are more familiar with the logic designs from the circuit also you can use an RTL designs and using FSM. And also you can use the by using the customer processor IPs also you can make it our RTL designs. Okay, all these methods to do the RTL designs. So one small example I given here. So you have a clock and input and current status and next state and output. By using the combination logic you can make it on small designs here based on your clock and your input. The combination logic will have presence and comes and it will give the output and it will in the from the circuit you will have a feedback here to the current state to the clock, right? So what are the designs methods you have using in RTL? So as I told you, VHDL, Verilog and System Verilog. So VHDL and Verilog and System Verilog. So nowadays System Verilog is mainly used for the verifications rather than the designs. You can use for the design also, but in the verifications you are using System Verilog more because of their flexibility. And you have verification methods also are there. You will look around that. That VHDL and Verilog difference is meant. So earlier all companies, industries using VHDLs. Nowadays also PSUs and means government companies and defense projects and aerospace projects. You are doing in the VHDLs. And commercial and small codes you will doing in the Verilog. So Verilog is the almost based on the C operators. By using the C operators, you can do the Verilog codes. In VHDLs, you have to have the number of libraries. I think everyone knows about VHDL and Verilog. Okay, you are using also. So VHDL you are using by writing the codes in VHDL means you have to add the respective libraries. If you are using the mathematical operations, you have to add math library, isn't it? If you are using incremental and any adder and subtractor also, you have to use math operations or unsaid operations. If you are using signed operations in your designs or logic, so you have to use signed library in the code. But in Verilog, you don't need to add any library in the designs. So it is almost in the similar to the C. So all the C, some of the C operators you will use in the Verilog. So this system Verilog comes after that in Verilog to system Verilog. It's an updated version to the Verilog and it is a own and very new operators will come in system Verilog. and almost in the as with the C coding. Okay. So here I mentioned two codes, very HDL and Vanilla. It is a counter, 4-bit counter code. So yeah, as I told, so you have to add the number of libraries here in the VHDL. This in the left side is in the VHDL code and right side is Vanilla codes. You have three main parts here. One is a library one. After that, you have an entity counter. It is a port declaration is done. In this port declarations, you will declare the input output in the designs. So clock reset is the input and count out is the output of the design. So clock reset in HT logic. So I mentioned here the HT logic keys and here out count out HT logic vector 3 down to 0 means that in my clock reset is only 1 bit. Okay, so that's why I mentioned here only HT logic, but counter output is 4 bit 3 down to 0. So I mentioned here STD logic vector. It has a 4 bit, so 3 down to 0, 3 2 1 0. That is counter to 4 bit. So if you are using a number of bits more means you have to mention here STD logic vector 3 down to 0 or 2 down to 0 or 7 down to 0. So 7 down to 0 means totally 8 bit and 15 down to 0 means 16 bit, 2 down to 0 means 3 bit, 1 down to 0 means 2 bit. So 0 also you count 0, 1, 2, 3 means 4 bit. Okay. Then the code declaration part is one is end counter. Then it will come to the reason or logic part. So after architecture, RTL of count and read signal. One signal took for the temporarily to store our design in here. So signal. So from here in the process, after process, we will start our actual logic here. So if reset is 1, then our counter will be 0. Okay. Once the raising as of the clocks, every raising of the clocks, our counter output will count by 1. Understood, right? So if reset is 1, okay, then our temp count signal declared here 0. So if this reset is 0 and the raising edge of the clock, every raising of the clock, our count will be increment by 1. Means up to it is a 4 bit. So 4 bit means it will count 0 to how much? 15. 0 to 15 it will increment by 0. In the first rising edge of clock it will count from 1. Second rising edge of the count it will count 2. And the third 3 and respectively up to 15. After 15 it will come back to again 0. Okay. And if you are declaring the if statement here and it will end at end process and till after all the count it will go to the actual output. Okay. See the count out is equal to temp end RTL. So you are declaring in the RTL. If you are using the behavioral, can you put here end behavioral like that. So it is a synchronous counter output. So you have a number of methods, a number of logics, a number of models also there in the VHDLs you can use. Within one example I given here is a synchronous counter. So and asynchronous reset counter also is there and up down counter also there and D flip flop also you can make it. So if you are using the D flip flop in the VHDL means you have to declare a clock reset and D. So D is only one bit output, right? So you can D output ST logic and Q will be the input and D will be the output. And here if reset is 1, it will Q will output Q is but 0 and if every rising edge of the clock it will be D flip flop based on your input output will behave. So same way I mentioned here counter or code in Verilog. So here I have not mentioned any library receiver. You can see here, right? So there is no any library receiver not mentioning, and it's similar to the C coding. So you are using input wire clock, input wire reset, and output raise 3 down to 0 count output. So input will are declared in a wires means interconnection between the two pins or two devices also. Okay, so all the inputs are declared in wires in Verilog and register based on your input and output you will declare in register. So this means it will temporarily storing our data. Temporary storing of data means output will count out, it will temporarily storing in the range. It is 4 bit, so we will declare 3 is to 0, so 4 bit. is always at positive edge of the clock. As I told here, so every positive edge of the clock, our count will start. So if reset is 0, so if reset is 1, then our counter output will be 0. So here 4-bit binary output. I declared in binary format. So here I mentioned as a B. 4-bit 4 slash bit B means binary and zeros. 4 binary zeros. Okay. Else if reset is 0. If reset is 1, output will be 0. Else, if reset is 0, the count will start from the every positive edge of the clock and end model. This end is based on your if statement. Understood that? This is a very small counter, and this is very important in the interviews. So they will say write the octal codes using the UHDL counter, and if is very important in interview questions also. Okay, that's why I mentioned here UHDL and VDL codes. System Verilog for the design should be same. So based on your input, you can write it here. Sorry. System Verilog also, so input instead of wire, you can use logic here. Input wire reset and wire clock and output is count you are using, right? So in the design you can use logic here. So they have a new data type in system Verilog. You can use logic, okay, instead of wire and rails. So you can input you use for an input as well as output logic. Okay. So one FPGA board specifications I told, as I told, we have a number of LUTs, number of DSPs, and number of input outputs and memory, and they have a one specific display and everything. So one FPGA present features I mentioned here are X7 Xilinx FPGA board features. So that package size is Xilinx SCR735T ATX7 FPGA IC. It has a 256 MB SDRAM. Okay, so it's SDRAM also it is there, it is 250 MB and 8 MB SPI flash memory. As I told you, so the FPGAs you have one flash and SRAMs, and also so onboard nowadays I told you it will come USB JTAG. So it is in a Xilinx FPGA, so they are using JTAG programmer. Okay, USB onboard, it is inbuilt USB JTAG programmer. So you can from the USB cable also you can dump or fuse your design in the FPGA board. And also you can use in the USB to UART conversion interface also, and it has a one SPI TFT display also. Okay. So any questions and answer we can discuss. Hello. Any question and answers? Hello.
Excuse me. Yes, sir.
Yeah. Any doubts means you can ask me. So we can hear.
Sir, like USB JTIC programmer means it's in what it is programmed? The JTIC
Once
programming.
your design is done, right? So after designs will convert in a bit file. As I told you can convert in a bit file. After the bit file, you have to dump to the FPGA board, right?
Yeah.
It connections between laptop as well as our board, right?
Yes, sir.
So it's called a programmer, JTAG programmer. If you're using the Xilinx, it's called a JTAG programmer. And if you're using a Quattros, means alter FPGAs means your USB blaster. So if you want me a second, so in better. This is a programmer connector.
That means it's already programmed and which language it is already programmed and how it will interface with our board. That's what.
Based on your design. So as I told us, now I explain one counter coders. So you want to
Yeah.
check the counter code in your board means that code will make and convert in bit format, right?
Yeah.
So after bit format, you will look at and you will interface our FPGAs by using the pin. You will assign the pin configurations. So once your configuration is done means you will also have in FPGAs in 4 LEDs, right?
Yes,
So
sir.
let us take 4 LEDs. So based on your LEDs, our counter will increment. Based on our counter code, the FPGAs will assign one counter 0 will be one LED and counter 1 is another LED. And like that, 4 LEDs and 4 bit counter. All the counter will work with based on the clock, as I told. So in the first class, the 1 will come. In the second class, 2. In the third clock, 3. Right? Based on our counter increment, based on our clock, all the LEDs will blink. Based on if it is in the 4 LEDs, means in the 1 means only one first LED will blink, other 3 will be 0 because 1 is in the binary means 1 0 0, right?
Yes, sir.
In
Yeah,
2
got it.
0 1 double zeros. In the 2 means in the second LED will blink, remaining first and 2 and 3 LED will be off condition, right? So like that you can check with our counter program. If you are deep or if you have any designs, you may processing designs, any communication designs, also you can make it. Check it in your.
Yes, sir. Thank you, sir. Okay.
So here you seeing, right? So all these are JTAG visible, right?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, I think in the lab you can see it here, programmable cable USB 2. So here is an Xilinx JTAG connector. So from this you can connect to the FPGAs. If you see the look, practical means you can understand easily. If any time consists in the next week, I can explain practically one like counter or any other designs. It's a JTAG. Okay, so USB means here USB. So for this USB using for the Altera FPGAs. Here USB bus for Altera CPLD FPGA programmer. So particular FPGAs. So you are using Altera FPGAs means you have to use this USB blaster. So if you are using Xilinx means it's less than sure, right, earlier. And this Xilinx JTAG connector or cable we have to use. So nowadays, as I told in the presentation, inbuilt JTAG connector will coming, so you can use directly this type of USB blasters because they are inbuilt of JTAG connector will connect in the FPGAs boards, right?
Okay, sir.
Lattice also they have own connectors. See, we have a lattice. This lattice. So you cannot use this lattice for the alter FPGAs or Xilinx FPGAs. And Xilinx FPGA connectors you cannot use for the this boards, lattice boards also. Okay. You have pins, pin connectors based on the board. You can connect and you can dump to the FPGAs. Right? Any doubts?
So Viru, you have seen our FPGA boards installed in University of Oregon system.
No, sir, I didn't.
Oh, you didn't join the call. Okay, unfortunate. So we have 5 FPGA boards already installed on University of Oregon system. On a day 3, the students have got access, and we have set up everything by default, and only they have to basically upload the microwatt, the open power code, and run it, and it worked very well too. So I may want you to experiment that. Maybe when you get some free time, let me know. I can send you the access details, and after that we can do some enhancement there, like a kind of a FPGA cloud. We can set it up. I'm also planning to have another five more FPGA boards there. So if you have 10 FPGA boards, suddenly we can do wonders there with all the
Sure, sir.
change.
Do it, sir. Actually, I have two FPGAs, Lattice FPGAs and Xilinx FPGAs. Currently, I don't have. If you have means, I can do it now itself. But currently, I don't have. Now I am came to my relative home today.
No, that's fine. But we have online the FPGA boards available for us exclusively for us to do training, research and development. It's like we have, we have done a lot of investment there.
Sir, we can do it, sir. So tomorrow or day after tomorrow, so Saturday, Sunday, I have free. So if anyone send means you can send the specifications of FPGAs means I can work out on and next week onwards we can do it some work on
Yeah,
that book.
it is for actually, many students also like, can get access to that, add a
Okay.
few things, on top of that.
Yes.
They can clone the microwatt code, and, they can make changes to it, and then they can deploy it in a FPGA board, and get, the full, the experiment, kind of a complete hands-on, continuous hands-on, not
Correct.
it's basically continuous integration and continuous development, CI/CD kind of a methodology we have to bring in, and where we can bring in all our things, like like we have verification, right? All those stuff, we can put together a kind of an environment there, a development environment, design and development.
Yes, sir. You can do it, sir. No problem.
Yeah, industry wise, how industries, like I know you are an industrialist,
Yes,
and
sir.
startup, you're working in a startup, and how industry is looking at it, all this FPGA experience, with the course development and all the stuff, simulation and all the stuff would be very good for the students.
Yes, sir. I can make it, sir. No problem. I can work it on that.
Yeah,
You will send me the details, what are the FPGAs are in there. So 5 FPGAs details, and then from that I can
I
make
am
it.
I'm sending it to you right away.
Yes.
You can take a look later
Yes.
and see how you can make a progress with this. Sure.
Sure, sir. Okay.
And any other questions, team?
Yes, so if there are any other questions, please type in the chat box so that these can be taken up by the speaker and then we can proceed.
Once again, can you please elaborate the speed offered by the FPGA boards as sometimes it's started with FPGA slow? So sometimes FPGAs are slow means based on your designs and your clocking delay. So if you're using the clocks in the FPGAs, right? So based on your clocks, the FPGAs will get slow. And utilizations of FPGAs. So you have as I told, one FPGA, RTX and FPGA 250 MB SDRAM, right? So if you are using 256 MB FPGA, full utilizations of FPGA board means the FPGAs board will get slow. So maximum utilization of pages is only 70%. Okay. So rest of 30% will be free means the pages works faster. Okay. So 256 can be FPGA board is there means, so less than 200 using your FPGA design means the FPGA works speed. Otherwise it will be some slow. Okay. Anything else? Can you please elaborate on that? Understood, right?
Yes, sir, understood, sir. Any other questions from the participants?
Have we any taken questions?
No questions? Okay. So thank you very much, sir, for enlightening us with such a good topic. I think this topic is really very good for all levels of the listeners, UG, PG, PhD, everyone. It was really good topic. So on behalf of EICT Academy MNIT Jaipur, I am thankful to you, sir. Thanks being accepting our invitation for being an expert speaker for this talk. Thank you, sir.
Yeah, thank you,
Yeah,
ma'am.
thank you, Menka, supporting this. Actually, Viru, like, thank you for this, and definitely we have to expand this,
Yes,
to
sir.
do
Sure, sir.
some
I will
kind
do
of,
it.
a kind of a FPGA cloud center of excellence with all these EDA and PDK tools, we can bring in, and put together a plan around this.
Sure, sir. I will
Certainly.
do it.
I think I got some ideas about it also. We'll talk about it, and
Yes.
we'll see how this could be helpful to even this set of students, within this shorter period of time, whatever. It's like kind of a journey, like the last 4 days,
Mhm.
and this is the fifth day we have been engaging with this set of students and faculties. And certainly next 5 days, we are going to have lots of speakers and, lots of practical things also. But along with that, we can extend, how do we do continuous integration and continuous development with all this platform, and that's a plan, I'm going to have. So let's see how we can
Yes,
build
sir.
this. And also,
Yeah,
like, we have Friday, all the participants too, like, Friday every day, I mean every Friday around 9 o'clock Indian time, and now 11:30 on 11:30 a.m. Eastern Standard Time, USA. We have a worldwide call to discuss about open power platform innovations. On top of this platform, what are the things one can do? If you are available, please do join. I will send a note to your participants. I'll send a note to the organizer, and they will share it with you. And there are a lot of things, you can learn, many things going on around the world. We
okay.
have participants from US, Europe, India, and other countries too, Japan, and all those people.
Okay,
Okay.
sir. Yes, sir. Okay. Thank you so much, sir. Yeah.
Okay, thank you. And
Yeah.
yeah,
Thank you, everyone.
Thank you,
yeah,
sir.
yeah. Let's
So
wait
shall we
for a
take a
few more
break for
minutes,
five?
for the yeah, for a
Yeah.
few more minutes, for the next speaker to join.
Yeah. So
Is
can we take a break for 5 minutes or?
Yeah, we can take a break for 5 minutes and then come back.
So yeah, so after 5 minutes, we are going to start it again. Thank you so much, dear participants. You can just have your snacks and something so that we will be starting again at 11 a.m. Thank you.
Yeah. Thank you, everyone. Have a nice day. Yeah. Bye.
Thank you, sir.
Hello.
Yes, sir. Welcome,
Dr.
sir.
Dr. Shashidhara, thank you for joining. Welcome back.
Thank you. Thank you, sir.
So the students are right now, on a break for 3 to 5 minutes. So you can set your PPT and everything.
Yeah, yeah. Sure.
Yeah.
Hello, everyone. Good morning and welcome back. Am I audible?
Yes, you're audible.
Thank you, sir. So now our next speaker, Professor Shashidhara HR, is here with us, and he is going to take the next session from 11 to 2. So he is going to explain SOC verification, and Dr. Shashidhara HR is here with us. Thank you, sir, and you can take it into slideshow mode, sir. Welcome back, sir. Thank you, sir. It's over to you, sir. Dr.
Thank you,
Shashidhar.
madam.
Thank you,
Thank you,
sir.
madam. Thank you. Thank you. I think my screen is visible to you people, I think.
Yes, sir, it's visible.
Yeah, yesterday we seen the basics of the SOC components and its verification, basics verification. So the last part of the verification is with an the formal verification. So that is, so the majorly we'll use a binary decision diagrams. So I will brief about the binary decision diagrams. So and then we'll go on to the IP verifications. So with respect to that. So binary decision diagram is the representation, canonical form representation for your Boolean formulas. So you can take any Boolean formulas, you can represent using a canonical form. So the major motivation is to give much space and redundancy in traditional representations. The redundancy in the sense the flow, you can see that. So the signal flow, how it can be derived, it's those parameters, and you can have more compact truth tables. If you go for a four variable and higher variable parameters, so the truth table will becomes an complex. So you can make it more compact on that. So and it will be in a conjunctive normal form, distinctive and normal form. So you can segregate where you how you want and how you can make out. So which will be constructs and a tree. So that tree will be called as a binary decision trees. And so normally all the binary decision diagrams so will be represented through a binary decision trees. So which is normally an ordered form. So those type of BDDs will be called as an ordered BDDs. So which is more efficient with respect to an efficient with respect to an operations. So and the representation maybe use more optimized values for those parameters. So these are normal 2-bit comparators. So I'm derived and a binary decision trees. So so initially I will take only the one value, a value, so a bit value. So if it is compared with other parameters, so then it will be derived. If it's not equal, then it will be derived as a 0. If it is derived as a 1, so then it will be if it's equal, then it will be derived as a 1. So similarly at the second bit level, so the B1 bit level, again it will be compared with the respective bit, and it will be derived if it's equal and not equal with a next bit level. So it will be goes on doing it. So finally you can have a representation of an equality and a not equality, so of those parameters. So these normal 2-bit comparators, what you are taking A1 and an A2, so B1 and a B2 will be compared. So the first MS bit of the first number, so will be considered and derived with an 0 and 1, and next bit will be taken, next number MS bit will be taken, and it will be considered with an 0 and a 1. So goes to the LSB bits represented with 0 1 0 1 values. Lastly goes with the second number LSB bit, so derived their values. So if all the bits are not equal, so then it will be represented as an 1. If all the bits are equal, it will be represented as an 1. So with respect to what the value will be there, so that value will be represented. Let us say, so I have A equal to B1. So A2 and B2 will be not equal. So at that time, so the not equality will be represented here. So this is normally represented with a binary decision or goes with an ordered BDD values. So that is the representation. So if you want to make more ordering, variable ordering, so I will just go on representing A1, A2, B1, B2. So A1 will be less than A2, A2 will be less than B1, B1 will be less than B2. So at first number with the 2 bits will be compared. The second number 2 bits will be compared. So both will be compared. Both numbers will be compared at a time. So with respect to that, here you can see that so the constructed graph is having a more number of variable in the tree. So that variable representation is minimized. So with respect to your ordered values, where is the 1 will be there, where is the 0 will be there with respect to that. So if all the bits are not equal, so then it will be 1. If all the bits are equal, then it will be 1. So otherwise, the representation will be 0. The representation will be 0. So if you have a n number of bits, so then the n number of representation of these variables can be considered. So I am optimized only at the lower level, at this level. So you can optimize at the second level also, at this level. So to make more reduction in the variable values. So if you have an n number of values, each number of values can be derived for their appeared values, that is 1 or a 0. So if I have a1, b1 and an up to an an, bn, so which gives an 3n plus 2 vertices. So the 3 is the number of representation where it should have to go. So n is the number of variables you are using it, and 2 will be the 2 possible vertices, that is 0 and a 1. So it can be modified so by representing only the first number comparison, first number bits comparison, and the second number bits comparison. So such that it will becomes a1 to an and b1 to bn. So which gives 3 into 2n minus 1 vertices values. So if you look at on if you look at on the applications of the verification, so which will be goes with respect to an equivalency of the combinational circuits. So majorly we will check the equivalency of the combinational circuit, so which will be specifies the normal canonicity property. So if f and g are equivalent, their bdds are identical. For f is a one function, g is a one function. So if both are equal, so then your bdds are identical. So for the same variable ordering, you can convert so those values. So let us say f will be is equal to a bar bc plus abc plus a bar ab bar c. So similarly, so we have g is equal to ac plus bc. So these functions can be derived as an so a, b, c and values. So similarly here also, so the a, b, c ordering will be done. So such that both are equivalent. So at that representation forms. So functional, so what is the advantage of this? So you can make out the one function, derives the functional vector for this function. The same test vectors can be applied to so these values also, these functional values also. That is the major advantage or major application which is derived from an ABDD values. So the one value which is generated are functional values, so functional test values, so which is generated is a satisfiability analysis. So where the boolean so will takes the satisfiable analysis so with respect to the ordered values. So let us say so I want to test for h is equal to 1, so or h is equal to 0, so with respect to the functional appearance, so we need to find the path for this 1 and a 0. So let us say I have I have the previous f values a, b, c, 0 and 1. So now I will take the path for an A1. So which is goes from AB to an A1 or ABC to an A1. So similarly, I will go for 0 values. So A to an A0 or A, B, C to an A0. That 4 paths which is derived to represent the 0 and a 1 will be expressed with respect to the satisfying solutions. The satisfying solutions are A, B, C. So there is the one value. So and A bar is the first value plus A, B, C values, right? Sorry, A plus B, A, B, C values. Similarly, here it is A, B values. So you can simplify this furthermore to see the test vectors, how much it can be taken care. So you apply what are all the functionality one. So let us say, so I want to see it for stuck at 1 at A, stuck at 1 at A. So I can make out this function to be appearable or to take the test vectors which is satisfiable to this function for the stuck at 1 values. So that is an AB function. So that is an A bar A, B bar C function. So both will be appearable. So at that end. So what is the, so in the last class somebody asked about the formal issues, formal verification issues. So the issues what all we have, so can be taken to a modeling function and can be derived it. So the major issues which is seeks at a model checking is a completeness. So if we have a property or if we are given a property, that property will be checked for their appearances either through an model checking or through an equivalence checking or through an BDD. So in all the model checkings, we will seek that property to be very effective and very representable to those values. So, and it will be impossible to guarantee that the specification covers all the properties the system should satisfy. So we are not taking, so all the functionality. If I take these functions, so I can't say that. So I can cover A, B, C, or I can cover A, B, or I can cover these two functions values. So that is with respect to what property we are defining and how it can be processed. So, and another one thing is all the properties what all you are defining it, so may not be satisfiable at the another one end. So some of the properties may be satisfiable, some of the properties may not be satisfied. With respect to which property is satisfiable, so you need to see the completeness of that. So possibly or theoretically, we will see that so all the properties what all you are defining is a satisfiable. So with respect to that satisfiability, we will write a specification. So that specification is similar or it should be comparable with respect to the user spec which is taken care. So our responsibility is to match the spec which is generated to cover all the properties to give the higher completeness, so with respect to the user specs. So another one is the negative results. So the negative results is with respect to uh, incorrect modeling. So giving an incorrect specification, we call it as a false negative. We thought that the property is matching or the property is appearable, so to the satisfactory, but so that property may not be matches to that. So let us say I am using an A plus BC as a property. So that property may not be appearable to my specification. So such that, so it will goes to an incorrect specification, which that those properties will be called as an false negative properties. And if you are defining the large number of uh, coverages or large number of properties, so then there may not be and you have a time to check all the properties. So there is a failure to complete the check. So that is due to an too large values. Here's another one. So the third one is a capacity. So your explosion, so for an complex systems is represented with respect to an state space factor. So these state space explosions normally seeks the more number of vectors, test vectors to be appearable through your model values. So if you have n number of those type of test vectors, all the test vectors may not be useful to your models or to your design. So at that time, so your complex system is unable to go to an higher accuracy values or higher coverage completeness values. So at that time, so we'll seek what all the useful test vectors are there. So only our models are there. So those models only apply to your uh, um, completeness or model checking values. So these type of model creation so will be called as a complementary technique. So where you will seek the only the appeared values to be tested, so which use the higher completeness for the SOC verification. So in addition to that, we can have an simulation, testing, emulation, etc., etc., etc. So that is about the model checking. So through a normal verification techniques and an ABDD technique. So coming to an equivalence checking. So equivalence checking is comparing your described model with respect or your design model with respect to a reference model. So normally it will be compares the implementation to an RTL model to an a gate level or RTL to an RTL or gate level to an a gate level models. So one can be existing and another one can be describable. So the existing will be the reference one, the describable will be the tested designed one. So you will check for only for the functional equivalency over there. So let us say I have an existing RTL. So, and I'm going to describe a gate level description. I will check the RTL existing model with respect to a gate level description for their functional equivalency only. No timed parameter will be considered. So the RTL versus synthesized gate level implementation so can be seen. So the RTL netlist will be compared with the synthesized gate level netlist. So if both are functionally matching, so then there will be an equivalence check passed. Otherwise, the equivalence check failed. So if you have a gate level design, you take an gate level design description and take the revised gate level design, compare those two for their functional equivalence. If they are appear, so then it will be said as an equivalency checking passed. Otherwise, no. So to do this, you can use an BDDs or you can go with normal comparable equivalence checking also. The better way is to use the BDDs. So where the canonical representation of logical functions will be seen. So that logical functions will grow exponentially with the number of inputs, so which will be considered, which is depends on variable ordering. So there may be a one-to-one or one-to-many mapping can be used to describe those values. So the equivalence checking goes with an will have the features which will be takes no test vectors or a test bench which is required. So because you are comparing only an functionality parameter, as you are comparing only a functionality model, so you can handle a large design parameters. Okay, you have a capacity to the tool. You have a capacity to handle large designs, which eliminates gate level simulations, reduces the time to market parameters. So equivalence checking will be used, as I said, with an RTL to RTL, RTL to netlist. That netlist is a gate level netlist which is generated, or gate level netlist to a gate level netlist. You can have RTL to an RTL, which is described model compared for a functional values. So the netlist to an RTL can have the functionality model which is described at the synthesis level. So that can be compared over here. The netlist to netlist so will be again the synthesized model at the gate level and can be utilized for the functionality checking. In these three, we can have some optimization can be described and can be converted, can be compared to see the equivalence checking values. You can make out thus that optimization at an SCTS, which is inserted at the netlist and make out. So constraint parameters, or you can go with a scan chain inserted netlist. You can go with an post layout netlist, etc., etc., etc. So as we described, the functionality checking is only to comparing the functionally equivalency between the two circuits. So if they exhibit the same functional behaviors. So if I am taking a combinational circuit, I will compare all the functional input values, all possible functional input values. So with respect to an output values. The derivative at the combinational logic will not be seen for those cases. In a sequential logic, so we'll take all possible inputs in a sequence. In a sequence, it may be a feedback or it may be only an independent inputs, etc. So we will not consider the output. The output will be seeks only at this feedback path. The majorly, the combinational circuit equivalence checking only at an input end and in a sequential circuit. So the equivalence checking only through this present state and a next state values. That is through a defined transfer values. So what you are making to compare over here. So the combinational equivalence checking will do with a function two approaches. One is called as a functional approach, where you are making out your output functions to be transferred into an BDDs. So if the two BDDs are identical, so then we will say that the two circuits are equivalent. So if we are defining a function f is equal to a and b, and you derived a BDD, you compare that BDD with another one function with an a and b values. So then if both functionality is equivalent, so then I will say both the circuits are equivalent values. So in a structural approach, so we will have a structurally similar internal input values. So we'll internal points. So maybe in a nodes, let us say I have 4 ports here. So I'm taking an NOC example. So the NOC will have 4 directions. So I have 4 directions: north, south, east, west, and a local 4137. Local. So if I am taking this and if I am connected a router point to every node, what I have. So now I will check out. So the comparison between this point to this point. So if both are structurally same or structurally similar, so then I will say there is an equivalence between east and a west. So now what I will make, I will derive my approach, my values to the west. The same will be applied to the east values. Similarly, between a north and a south or north and east. But anywhere else, the local will not be compared in NOCs because the local will be connected to the local the P values, process element values. So, and it will not be taken care to explain or to make the comparison of this. So that will prove all the cut points which is there at the input end or internal points end. So which will be an equivalent. So you can make out all are equivalent or you can make out some are equivalent. That is with respect to considered So the BDDs of output functions must be identical. So using the same variable ordering for functional equivalence. That is with respect to how you can consider these parameters to be appearable. That is north, south, east, and west. So where and all you are putting a cut point to describe those identity will be derived. If BDDs are too large, so you can't construct the BDD, so there will be a memory problem. So because you need to store all ordered variable values, so that you require more memories. So such that what you will use it, so you will partition the BDD into any different parts. So you can have the n number of BDDs. So the n number of BDDs can be cut down to an respective points and make it in single ordered values. So all those single ordered values will be taken, or all those smaller pieces will be taken into your uh, consideration, so that your BDD becomes very small. So you can have that smaller pieces, you can decompose that, and you can represent each piece into a separate BDD, and you can check that separate BDD for equivalence values. So each piece to each piece you can compare, each segregated or cut down PTD to a cut down PTD you can compare, and you can derive the functional equivalence on that. So you can check out the functional equivalence parameters on that. Similar to how you can make out the two different the big problem into a smaller problem, system into a subsystem, subsystem into a block. You can make out the block to block compare if both blocks are same, so then you can derive it as a single block. Similar way here also, you can cut down your BDD into a smaller BDDs, and that smaller BDDs you can decompose it and that each one as in a separate BDD and check for an equivalence for the internal points. So the decomposition of each functions into a functional blocks, so which is represent each block as a BDD. So one block as an a BDD. So this is the function f, this is the function g. So I will take the function f. So there is an two internal function f1 and f2. So I have a two inputs for this x and a y. So the intermediate node which is derived as an intermediate point as an z. So which is goes for that. So now I will represent the BDD of f. So with an two segregative function, one as an f1, the second one as an f2. So the f1 will be derived uh, with respect to that. So I will say, so z is equal to f1 into x. So similarly, the uh, f which is derived will be equal to the function of z and an f. Z and ny. So now I have two separate BDDs. So this is the one BDD which is represented. This is another one BDD which is represented. Similarly, I will go to the G function. So I will make the equivalency. So again, I will derive the Z. The Z is so G1 of X, and similarly, so G will be is equal to G2 of Z and Y. So now you compare this with this and see the functional equivalence. So both are same, only the change is the derivative, the functional derivative. So that I can say there is an equivalence. So similarly here also, if I compare this one with this one, so if both are equivalent, Z and Y, G and F, so both are equivalent, I can say both are functionally equivalent. So here I'm defining a cut point at Z and I'm deriving two functionally equivalent values. So one is at the starting at a primary inputs, and another one it has a higher values, and comparing their equivalency how we made it. So the cut point resolutions, all the pairs of the cut points are equivalent, that is f is equal to g. If intermediate points f2, g2 are not equivalent, the functions f and j may still be equivalent. That is a false negative. Let us say, so I made it this as an z1, this as an z2. So let us make that maybe a cut point which is derived. So because I derived the cut point differently here, z1 and z2. So now what I will say, so I will just compare these two and I will say f is equal to g. F is equal to g. but internally the F2 and G2 may not be equal because there is using a two cut points which is different, Z1 and Z2. So these equivalency will be called as a false negative equivalency. False negative equivalency. How to check this? So you can use your XOR gate, so which is derivable. So normally, so if the XOR gate is when both the inputs are same, so the output will be one. Otherwise, the output will be 0. A similar way you can check out for the XOR gate. So the XOR of F and G functions, so which is derives as an a BDD values, so which shows the equivalency between the F and a G. So if both are same or not. So with respect to that. So in a structural equivalency, we'll take and two circuits, which with its own structure. We'll identify the similar cut points or internal points, call it as an cut sets. So we'll exploit all the equivalencies for those cut points. That is the internal equivalencies of that cut points. And we'll find it out what all the parameters needs to be there. Let us say if both ABC and ABC are equivalent, what they are appearance. So let us say I consider an A, B, and C. Here also A and B. So now I will exploit the equivalence between A to A, B to B, C to C. So if A to A is equivalent, I will say it is an equivalent. Otherwise, I will say it is a not equivalent. So there's still a negative problem, false negative problem may arise. So I can say F and G may be an equivalent, but differ structurally. Let us say, so I will use F as an A, B, C plus A bar, B bar, C bar, and G as an AC plus BC values. So if I optimize this also, so I won't get this. So, but equivalency values, the derivative logical functional equivalency values may be the same, but the structurally there may be any different. So this is also a false negative problem. So false negative problem. So, but while verifying it, so we need to declare, so what is the difference from F to an a G or G to an F. So such that, so we can see the better implication techniques for those values, what is the difference values, and we can make out more and more appearance based learning so that we can apply for this. Still, we have more chances to derive more equivalence, more verification algorithm on these equivalence part, and you can derive it more values also. So go with a sequential equivalency, so which is represent each sequential circuit as an FSM, normally which is derived as an FSM. So that can be goes with a communication FSM also. That is a better way to represent, to check out the sequential circuit, or you can go with an ASM techniques also. So there is also another way which is takes to represent the sequential circuit. So in sequential circuit, we will verify all the FSMs for their equivalencies. So if I take two sequential values, and so if I make that to be represented, so then I will verify the two FSMs which are equivalent or not. So the major approaches are reduction to combinational circuit, isomorphisms of state graphs, symbolic FSM of traversal of product machines, etc., etc., etc. So that's about the equivalence checking. So we have some of the formal verification tools. So I think yesterday's I discussed some of them. So we have a model checkers, we have an equivalence checkers. So we have a separate academic research tools. Some of them are open source. So we have some of the commercial verification tools also. So I think in the yesterday's class, somebody asked about the tools usage with a Python to convert it to an Verilog. Some of the academic research tools so can be utilized for that, because that is an open, your MyHDL is an open source, you can utilize it. So over that. So we have some of the commercial verification tool also, so which is more binded to those factors. So your cadence is the one, your synopsis is the another one, mentor graphics, all are commercial verification tools. So we have a segregation in a formal and a semi-formal tools also. So that also can be taken care as an open source, and some of them will be a semi formal. Okay. So these are yesterday also. So we have an SME, we have an Mosha, WIS, and High Tech. So that is from Berkeley University. STEP, Stanford University, SGM, CCU and Sinica, Red Academia Sinica, Upal, Uppsala, and Aalborg universities, Cornos, Verimax. So some of the tools. So we have a formal check with an cadence, formal medal checker with an Avant, formality with an synopsis. So formal pro with an mentor graphics, black tie and conformal LEC with an Verplex systems. So I think this is already I discussed in the yesterday's class. So what is symbolic model verifier? We have in cadence. So if you are using a university bundle, the SME will not be available. So you need to go with some advanced version. Research bundle will have an SME versions. So if you have a research bundle of an cadence, so you can utilize that. So that is very good tool to do the model checker, model verification. So we have some success stories to define that. So supports SMVL and an Verilog with an VLS to SME. So there will be a problem size reduction also, scalar set, data type of symmetric reduction, ordered set with an data types of induction, subclass structure of the class splitting, layer structure of compositional assume guarantee verification, etc. So many appearances can be seen with an SMB tools. SMB supports only one implicit clock. You can have a clock distribution inside to that. You can construct a CTS over the clock, clock distribution over there. So with respect to your appearing techniques, you can design that distribution and you can make out that to be describable there. Issues in modeling in SMB is multiple clocks. You can have multiple clocks, gated clocks, unsynchronized clock, and unsynchronized clock. So that depends on how implicitly you are adopting so these values for those parameters. So I'm just giving a glimpse on the tool. So general strategy for model verification, you define what to verify. You need to create a model there. Maybe in a design module to a test module. So what you want, so that should be defined particularly. So you need to construct the environment which is required for verifying each property. You need to define a property, what property needs to be checked, and you need to give the environment for that property. That is a major end. So because once you create a model and you define a property, so if you are not defining an environment, so or if you are not constructing the environment, so that model will not be appearable to the tool to check for that. So that's why so you need to create the environment also. So for that, let us say I want to test an AND gate. So 2 input AND gate. So I want to create the AND gate as an ADUT. So I want to create a test for an ADUT AND gate. So now I want to create where to be test and how to be test. So I will give a property. So as an A will be appeared as a signal 1, B will be appeared as a signal 2. So A will be equal to 1, B is equal to 1. So A and a B, so many properties. Now I will check out I want to give some of the environment. So I want to push the A values and I want to check the equivalent model values over there, and I want to check out so for that. So each property can be transferred to a logic also, CTL logic also. So and you can make out the coverage of CTL properties over RTL code. So how much you are defining it. So now at this end, so you can have the time definitions what you are using. So you can go with a code coverage at this end. So you can define the property for the code coverage and you can utilize the code coverage property there. Or you can go with only the timing analysis. You can utilize the timing analysis STA parameters set that RTL code also. The similar RTL code can be taken care of. And environment what you are creating, it should be with respect to any one of the things which is can be definable. So you can say that clock is 10 nanosecond. So and you check out the clock with respect to the created environment. Is it generatable? So is it appearable? So it is a 50% duty cycle, etc., etc. So the equivalency can be checked on those parameters. So the properties, so I'm just taking an example to define how your property can be looks like. So let us say I have a function g, so which takes an a all path as an a. So all my the paths are defined as an a p. My input is x, so the input appearable is an a q. That is, you are defining a validity for that input as an a q. So all x will be derivable only through the q. So that's why I will say x is a function of q. So if I want to define a path, so then all my paths are should be a to a. All paths should be x of q. So it should be derived from an x values. So if I want to define a function for a g, so then all the path I considered p values should be presented for the x of q values. X of q values. So that's why I will give p is a of a into x of q values. If the p does not occur, there is no path you are defining it. You can't check this because so your path is itself is absent, so that you can't check it. So model checker says it is verified as true. So because the g is presented, so at least we need to check if p occurs at least once, only at least one path is there. So if there is no path, so then the whole checking will be failed. So for you, so one path is there. So that is the a of g not of p is false. So there should be an one path to be taken care of. So fairness constraints, the correctness of the model depends not only on the environment, but also some specific behavior of the environment. You need to define it. So what restrictions, what constraints you are giving to say that this is a specific behavior. Let us say I have an input A, I will check it for a 10 nanosecond appearance for logical one. So that specific behavior, that constraint, the appearance, the A equal to 1 for an 10 nanoseconds. So will be the fairness constraint. So which says the model will takes the input A for that specific behavior. So you can define it for another time and higher time, and you can check it only for a 10 nanosecond also. That is also possible to be appearable. Or you can give the range for that. So like a 10 nanosecond to 100 second, 10 nanosecond it goes to a high, 100 nanosecond it goes to an low. So your assumable properties can also be presented for this. So these fairness or this behavior what you are specifying as a constraint, so will be the mostly called as or it will be called as an assumption in assume guarantee reasoning values. So reduction of address bus and a data bus. So there is one traditional approach. uh, Abstraction is 32-bit wide bus can be segregated into 1 bit or 2 bits wide values. So that is depends on how you can consider the data address bus to an data bus and how you can be representable. So not used in SOC because full data bus and partial address bus are used across so configuration registers. So reduction of address bus and a data bus. Why we are considering the majorly an address bus and a data bus, because so as the major SOC nowadays looks for the NOC component. The NOC components needs to be taken all the with respect to only these two buses, address bus and data buses. So that's why. So the major trend, major approach which is defined only with respect to so this address bus and data bus also. So divide verification task into two parts. CR accessing logic and normal operation logic. That depends on so how you can consider so the CR to an normal. So you need to construct at least two different environments. So where you can have and how you can define it. So as you are constructing at least two different environment, we need to have two different property groups also, P1 and a P2 or that property groups needs to define the n number of properties which is made it available to that. So incremental design and verification is a better way to go and make out these type of designs. Early stage of designs helps to find real design errors. Later stage of designs helps to find model and property errors. So as you move on with an verification, so the bugs maybe goes on reduces. So as you are making a model checking, so your time is reduced, the verification time is reduced. So for an SOC verification, so make out to be appearable. Formal verification of SOC is definitely required, but it should be used in conjunction with other verification techniques. So capacity of formal verification must be enlarged for its widespread of adaptation. So the techniques required is design abstraction, verification, partitioning. So this is about something on SOC verification. So if you have any clarification regarding this, you can ask me. Okay. So there is no clarification, then about pardon.
So participants, if there are any questions, you may ask. So, sir, there are no questions till now. You may start the next topic. Yes, sir.
Yeah. Thank you. So till now you seek on the SOC verification. So now we will go with some part of the IP verification. I'm not going in detail to this because it is a vast one, so we can't derive it in 1 or 2 hours to describe it for that. So let us look at on the basics things on this IP verification. So the IP verification, as we described, the SOC verification in different domain verification. Here verifications can goes with a cycle level. So there also we defined a cycle level. So we defined there also a transaction level. So here also we are defining a transaction. So there we are going with an hardware software co-verification. Here we are building a test bench to seek the verification. So hardware debugging maybe using an emulators as we described that. So maybe using an RPS for that. So I will just describe an example here, iPro. So may not be in detail. So maybe an abstractional view will check it out how the IP verification can be. So the major issues are use technique. All the IPs which are defined to be. So the test bench, what all you are describing it should be. So debuggability will be the major issue which needs to be considered with because every applications may be a different. What all the basic IP you are using or the normal described IP you are using. So may not be adaptable to the next application. So that we need to have a debuggability. See that. So test bench issues. So various test bench support needs to be there. I think in the next sessions, Shruti will describe the different test benches, how it can be adaptable. So those test benches, so those various types of test benches need to be supported. We can use higher level languages like C, C++. We can go with HDL, Verilog, VHDL, System Verilog, etc. So the standard is SAME, System C, OpenPower, and so on. So we can have variety here to do this. So some of the things are standards are which is defined for some of the IPs also. So various levels of test benches. So transaction level controlled by command level. So example read Cycle level control over pin by pin, one to one or one to many. So abstract bus level, so which is taken care to define those values. 1 second. The cycle level and an abstraction bus level.
Sir, your voice is not audible. Dr. Shashidhar, your voice is not audible, sir. Hello, sir. Am I audible? Hello.
Hello. Yeah.
Now it's audible, sir. Yes, sir. Carry on. Sir.
Yeah. So some maybe network dropping issues. So the cycle level and an abstraction bus level. So is with respect to interconnects, on-chip interconnects, how it can be taken care and how it can be processed over there. So normally the cycle level will take the control over pin to pin, which is definable from one end to the another end, maybe a global interconnects which can be definable. So the abstraction bus levels normally defines particularly on an NOC. So there is a standard on-chip networks. So you can have an NOC there. So and you can define it for the interfaces, NI interfaces, network interfaces. So which is segregatively seeks the local connections to a routable connections, maybe a north, south, what are defined north, south, east, and west. So normally it is an on-chip networks are in 5 connection ports. So one is a local, which is coming from an processing element. So maybe one processing element, one transceiver factor. So I'm going to the different directional values. That 4 different directions are north, south, east, and west. So and your abstract bus level. So that is the on-chip network should have to be described. So how you are defining the connection at a north to and a south, east to and a west, and to be describable to the routing values. So there is a major end where you can see the IPs. So maybe the router may be the common across that as an IP you are defining it. So but the level of communication from the local to these communicating paths may be a different. So that's depends on how it can be definable over there. So the cycle level verifications maybe goes with DUT, defined DUT, so which is majorly on another one end. So we have a test bench which is described here. So maybe you can go with C or an HDL, so which can be describable. So we have majorly a communicating between the DUT to an HDL. Normally, so will appear this cycle level as a repetitive model, so which is described so at different ends. This is my normal DUT, so which is communicated across your test benches, so through these factors. So if it is repeatedly appearable for a given time periods, as we described in the yesterday's class, so that will be considered as a cycle level verification parameters. So and all the test benches will be seeks the device drivers, so a simulation part, software simulation part, and created that the test benches at the driver level and maybe communicating to your DUT. The DUT can be an FPGA part or can not be an FPGA part also. So depends on where the applications will be. So normally looks at a microwatts with respect to an FPGA. There we look at the FPGA parameters also. So in between this, we're creating a channel that is called as an PCA channels. So between a simulation to an your microwatts or your where you are implementing it. So that PCA controller will take the buffer or a pin signal generator to the DUTs. So maybe incoming or maybe outgoing from the DUTs. So that DUT will be the segregative part what we are explaining here. Yeah. So software dispense modeled with HDL or a C language, as we described, generates stimulus at every clock cycle. That depends on how you want. Stimulus respect to the particular and it should be described at every clock cycle values, but every parameters which is taken care at that end. Check the results of the DUT for every clock cycle. There is a response which is captured and made it comparable with the database reference, and so we says that the results is derived correctly or not. So depending on that, you can say so how to change the stimulus values also. So that is a major end where your test bench will be looks. So and normally any test bench will have a three parts. So one is a declaration. So where you will seek that. Second one is an stimulus generator. So the third one is a controller factor or controller generator. So in a declaration part, you will declare all your IOs are called as an interconnects, local interconnects. The stimulus, so giving the values to this IOs. So the control actions may be deriving a dependability for to generate the stimulus. Let us say I used an initial in Verilog. So I will say input A is equal to 1, B is equal to 0. This is my stimulus. So if I say always at 5 nanosecond, at 5, clock will be equal to not off clock is uncontrollable. So that, so for this clock, every clock, so I am generating a stimulus. I am generating a stimulus. So that stimulus, so maybe seeks the derivability, the response derivability. Each response derivability which is taken at every clock will be checks for that results. So it will be taken care for the result values. So normally the hardware will be goes to define an DUT. Normally the software will be the test, the hardware will be the DUT. So maybe your design may be there in an FPGA or map. So all your functional values, so which is defined at a test bench, will be mapped to your hardware. Maybe used on system bus to transfer this. So, for example, you are going with those values, etc., etc., etc. All signals are assigned to DUT concurrently after they are transferred from the software test benches, one after the another, and you can go for checking it. So normally the speed will be depends on the simulation, or so depends on the FPGA what you are utilizing it. So normally it will be a software simulation due to an acceleration of HDL or a C model, which is determined which is determined by the interface requirement, number and a bandwidth of signals which is to be transferred, and the bandwidth of the interface, that is the PCA values, and can be derivable at another end also. So at a transaction level, so we will seek the same simulation parameter, but the same test bench parameter, but the different in an ADUT parameter. So there we are utilizing the buffers and a PCI controller. Here we are using a transactor to do the transfer of the signal from the PCI to an DUT. So normally these transactors will say when to which signal and when to apply to the DUT and when to take the response uh, to make an comparison. So normally, as you are making out to hold a signal for a while to make it appearable through the transactions. So that's why we need to have a more DMA parameters. So more DMA parameters. So that will be available with the main memory and maybe communicating with your test bench factors. So at a transaction level verification, we normally modeled test bench with an C language. So we will generate the stimulus. So there is no dependency in the clock here. So because you are making out an ordering generation, so that your stimulus will be goes on appearable. So that we don't use the clock to be dependability factor for your design. So and check the results of the DUT. Only information enough to form a transaction is transferred to DUT, like a command, address, and a data can be sufficient. Or you can have something, let us say reset equal to 1. So then you transfer or enable equal to 1, you transfer A to be there and A transact A and B. So when reset is equal to 0, you transact C and a D. Or you take one input A, whenever A goes to an 1, you transact the C and a D factor. And whenever A is equal to 0, you transact E and AF signal, something like that. So you can have the information to form the transaction which is transferred to the DUT. So the hardware is a DUT and a transactor, normally mapped to an FPGA. So as I told, the transactor will have a knowledge to see when to interpret the transaction and hence generate all signal necessary for the DUT parameters. It can be transferable at one end. So operating speed normally, as the software and hardware are works independently, so that the speed will not be dependent on either hardware or on a software. So, but generally, which is more faster than the cycle level verification as well as the software simulation parameter. So the automation techniques. So we can have SCAMI, Vera, and a test builder. So the API, the standard co-emulation API, that is a modeling interface. Software part implemented as C or C++ with a recommendation on hardware implementation. So based on the ICOS, multi-channel or co-modeling technique, called as a tip, transaction interface portal will be used. So the consortium funded in 2000 is SCA API, Apotex, Cover, ICOS, Mentor, ST Microelectronics, Synopsys, and TransID are the major partner, the consortium partner of SCA API values. So nowadays we are using 3 version, SCA API version 3, which is a modeling interface. So which is one is derived with an system C initiatives with an April 2001, which is now available. So and we can utilize this SCAMI with an system error also, auxiliary system error also, which is an interface technical committee which is merged with October 2001 and made it standardized also. So SCADI with an debug interface and SCACI with an a control interface and progress. So in 3 we have both DI and an SCI is presentable. So debug interface and an control interface also. So the Vera, so is a functional verification language for test bench description. So OpenVera site, so we have this openvera.com. So there is a language specification which is obtained. So it is similar to your system Verilog, which includes the HDL features like a clock, OOPS concept of system Verilog, sorry C++, or an which is which are all which is utilized at a system Verilog, which can be utilized over there. Bit data types and bit operation, extraction and concatenations can be utilized. Data expectation, do something when the expectation is hit. So 0, 100, bus dot acknowledgement equal to 1. That is indicates acknowledge must be 1 in at least 100 cycles. So which is carried on a bus. So normally, which is describes how your transactions will be made on each signals at what type, and what environmental values can be taken care of this. So Vera verification environment is a commercial product of from Synopsys. Vera source codes are compiled and runs with HDL simulators in which DOT is uh, simulated. So additional features we can have an ATPG is very good in Vera. So automatic, that is what automatic stimulus generations. We can do higher depth coverage analysis, and we can obtain more the coverage analysis also. So sorry, coverage efficiency also. So maybe it goes around 90 to 95%, or maybe we'll think on goes to 100%. This is the normal structure of an Vera. We have an DOT here. This is a simulator. So this is a Vera shell. We'll create the Vera shell. So under an HDL simulator. So this is a Vera source, which goes with a compiler, which is attached to the Vera shell. So to derive that. So, and all the headers, objects, and list will be defined, which is communicatable to the PLI. So the PLI will make the simulator to activate. So with respect to these values. So these are all things needs to be supplied by the. So these are all things is inbuilt or automatically generated, the tool generated. So similarly, if you're using an Xilinx Vivado, you don't need to write a test bench. You just say the sourcing. The sourcing, once you are sourcing the test bench, so the test bench for your DUT is automatically generated. So those things are these. Normally we look some those type of. So these are two are inbuilt values. There are PLA and Vera. See how to communicate to this. So the Vera source should be written. This is similar to a test bench, what we are written. This is your DUT. So these are the variable list. So the second thing is the test builder. So normally use it for transaction based verification. So functional verification in higher level of abstraction. So normally we'll develop the test from system level perspective, look at the higher level, and we'll develop that, because the transaction level modeling itself is seen at an higher level, higher abstraction. So we have a test cases which is designed, which is put it onto an TVM. There is a transaction. So your DUT will be there. All the transaction which is created from the test to an TVM or from the TVM to an test will be converted into an signal level once you are applying to an DUT. The communication between this to this TVM to an test will be called as a transaction level communication. So from the TVM to an design will be called as a signal level. Depends on how you can make an adaptability between these two values which is appearing. So the major advantage is which is enhances the reusability of each component in the test benches. So we can define which one is used and which one is not used also through your coverage analysis. So which improves more debugging, more analysis can be there, and more coverage analysis. This is the one type of test bench which will be looked. So we will build it with the test builder. So we'll use a C library, PLI and FLI. So this is using the transactor is designed using an HDL or using a test builder. Normally DUT is with an HDL. So we'll I am transferring the send pocket memory to an expect write. So whenever you send it, hold you write it and keep it the pocket. If it's not reached, then you need to send it back. So that's why we create memory expect write. So once it's reached to a transactor, it will be segregatively explains what are all the contents of that pocket. There is a header, address, data, etc. So that directly will be communicated to the DOT through the HD parameters, the address and data, etc. From here to here, we utilize the simulation. Here we utilize the C library. That depends on how adapted to describe those values. One is another one where similar or IP verification parameter. The functional test point automation tool by Varsity. Its concept is similar to Vera, but starts earlier and more widely used. Described user specification with E language. So we need to see that the interface spec and test plan by E. So you can have a legacy code in C, VSD, and a Verilog. This is the specman elite. It's automatically generated. We can have an ATPG, automatic test bench generation. So you have a comparator, test and data and temporal checking, and then coverage analysis. All the three is applied to DOT to make the analysis. So we can have a built-in logic analyzer. So there is another one parameter with an aspect called below. DOT boundary parts, DOT internal and internal PC, this is the iPro board. So we can have a communication between these. There is a PC. The schemes, so low speed scheme at less than 10 megahertz. There is no dedicated storage element in the device. All debugging information is transferred to main memory or large storage device at every cycle. So read back scheme of Xilinx device is typically example. So where the major one and where you should be looked. Usually the scheme needs only a small number of IO pins like JTAG pins, clock, TDI, TMS, and ATD. 8-bit parallel interface, clock, init, CS, read write, and data, 8-bit of data. So if you are going for an high speed, that is goes above 100 megahertz. So there is no several dedicated elements which can be internal memories or an external. That depends on how you segregate to who takes care of to explain so those parameters. So all debugging information is stored in the dedicated elements. So typical examples are Xilinx, chipscope, Altera, signal tap 2. What is iPro? So iPro is, as an example, I'm taking the iPro here. iPro is a small scale design verification tool by enabling C, C++, HDL, and a de facto standard interfacing APIs. So the proprietary for C++, C++ API, proprietary for Verilog API, API, or an MI API. This is a test bench. This is the normal structure of iPro. So test bench joined at REST blocks in C, HDL, or system C, IP in HDL and EDAF. So we will make an communication. The test bench is applied to an APC. So the IPs is applied, IP in HDL or EDF is applied to an FPGAs. We will communicate through an PCA bus for an verification. This is the normal iPro values. So we can have the running speed. So if you have a simulator, we'll run it on 10 hertz, 10 to 100 hertz. So if you have an accelerator, go up to 1 kilohertz. So the emulator will be 100 kilohertz to 1 megahertz. Rapid prototype will goes with 1 megahertz to 10 megahertz. Real silicon will goes to 10 to 100 megahertz. The iPro is, you can see there, all are will be in a short range speed parameter, but the iPro will takes, it's a card which will be takes the more speed value, that is from 1 kilohertz to 100 kilohertz. So the investment is also very less in iPro than comparing to the other parameters. So the typical usage is for an IP verification, we have a test bench. This is a PC. You put your IP here for an iPro, communicate that. So take the interactive IOs. So what you want. So this is the cycle verification test, automatically generated model. This is my iPro. This is a signal information what I'm giving. This is a signal which is for a DOT. Transaction level. So test transaction and DOT. Abstraction bus based verification. We have an BFM, which is create and bus FM values. It's a bus and different DOTs at a single end. You can see the structurally difference how the iPro will looks than other factors. So large size data at an PC. So we need to give more DOT factors there. So we have an iPro all the DPPTs can be put onto a multimedia boards like a mic, screen, speaker, etc. So the user design or your DOT goes with an Verilog or an VSDL. The test benches goes with Verilog, VSDL, or C++. We can nowadays we have a system Verilog also can be. So Linux version or Windows versions both we have. The standard C, System C, OpenPower, Test Builder, and API values. MI or API values. API C or C++, Visual C, Borland C. So GCC, GNU, GCC, Ardour, Segment, R goes with all varieties of Verilog. So all today's varieties also can be used. System Verilog also can be adaptable over there. So and all. So this is the host computer with a PCI card. We have an OS. So we have an iPro device driver, iPro API. Above that we will build. So your standards like an System C, OpenVera, Test Builder, and an HDL simulator. So above that your applications will be set. Your design, your test bench, and this. So once ever you want to communicate, then the application goes with a particular standard and makes it available to the host computer through an iPro devices or iPro APIs. So that is normally will be set on. So this is the normal design flow. Create a test bench. So for each test bench API will be inserted. So your design under test. So it takes to a third party synthesizer. Design EDIF. So we'll prove. We'll go with an builder, iPro builder. We'll for that utilize that to build that IPro parameter. Third party P and R downloadable data. So then you will target the board downloaded with the triggering the settings. So then we'll take that signal to an a viewer, third party viewer with respect to the test bench where your software label is embedded with the test bench. That so every stimulus which is effective to the IP what you are creating. So the same thing. So we'll go here, we'll come to this and goes to this. So we can have an appearable to this also. This is the compilation. This is the synthesis. So this is the P and R. This is the mapping by running the test bench. This is the debugging where you look for with the different parameters built in. So then we have an execution. The PC to an PLI. So cycle level with a Verilog, a simple this is a simple AL example I'm taken. So to see how it will be cycle level verification. This is my check card. I'm deriving a check card. So this is my stimulus, which is generated for different commands with an optional. So with the carry values also. So this is my ALU. It is having arithmetic block, logical block, multiplexer, and an for to do that the selection buffers. Step 1, start with the EDF of the ALU, need synthesizer. So any synthesizer, so you synthesize this. So DUT goes with iPro, there pulled on to the iPro. So make FPGA mapping of this data. Modify test bench by inserting the PLIs, where and all you require. So the PLIs, so modify that with respect to the given iPro values. Run the ALU with iPro and HDL simulator. That is with a test bench. This is at an host computer. This is at an iPro device. This is a one simple cycle level test bench example. So all ALU proxy is image of ALU. So I will see that card 0. This is that automatically generated iPro factor. So ALU proxy. These are the values I am giving. Signal right, clock advance by model. So mod HL underscore L, signal HDL underscore clock, etc. 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 So this is the automatically so generated by iPro softwares. So this is my initial blocks where I look for my stimulus to be generated. Reset P1 equal to 1. Positive edge of the clock, it will be 0. At 2 positive edge of the clock, it will become 1. So depending on the time factors, you are going on deriving it. So the SSRAM example with a transaction level with C. This simple SSRAM example. User test bench on a C is the IPO device driver. This is the PCI interface layer. This is my SSRM parameter. So these are the signals which is derived at input and so same thing. So need a synthesizer. Start with EDF of the SSRM. Map. Step 2, map PGA mapping data. Step 3, modify test bench by inserting the PLIs for IPro. Run the SSRM with IPro with and HDL simulator. This is normally host computers which will be taken care. DUT and the transaction will be goes on to these parameters. This is one simple example similar to that what we have derived in the previous examples. So I will skip this. The performance so provides outchunk speed over 2000 x values. So floating point number calculation of the IPs can be possible. So gate count can goes up to an 208479. Logic usage is 99%. Model sim only a lower values. iPro with model sim it is increased. So normally we'll design using a model sim for functional verification. If you use with an iPro, so it is increased at a rate of 47. So the iPro with a cycle level API with a model sim, so it will be increased with a 69. Transaction level, so it is a larger one for an IP verification. So this is what we require. So for an IPs to be looked at. So it is summary, easy to use and fast setup, time to emulation. So no or mirror source identification. The same test bench for simulation and emulation. Various verification code, cycle, transaction and abstract bus modes. Powerful debugging. There is a BILA you are using, built-in cell logic analyzer as a real hardware logic analyzer. High performance interface to software set, speed DMA features, high to low level languages such as C, C++, Verilog, and VHDL. Open interface systems, API layer provides easy to interface mechanism to de facto standards. Scalability, multiple iPro cards, as well as various gate count options are. So that's about a brief introduction on the IP verification. If you have any clarification, do ask me.
So, dear audience, till now, if you have any questions, you may ask. Do you have any questions so far? Please type in the chat box if you have any questions. Sir, there are no questions so far.
Okay, thank you. So I think Shruti is there.
Let me check, sir.
Hello, madam.
Yes, sir. Shruti is in the participants or panelist? Panelist, she is not here.
1 second, madam. 1 second.
Yes,
Yeah,
sir.
madam.
Yes. Shruti, are you there?
Madam, she is there in attendees. Can you make it as a panelist?
Yes, sir.
Shruti Ravi, I think, ma'am.
Yeah, Shruti Ravi.
Yeah, she's there.
She's trying from the long back, I think. Pantanodi?
Shruti Ravi.
Yeah.
Yes, sir. Done, sir. Shruti, can you
So-
hear us?
Yes, I can hear you.
Thank you so
Yeah,
much.
thank you so much. Yeah.
Shall I give him, give her presenter permission, sir?
Yeah.
Okay, sir. Okay. So now you need to stop sharing, sir.
Just trying it. How to stop the sharing.
Shruti,
Okay, okay. Yeah,
made you
establish my share.
presenter?
Yes.
Shruti, you are
Yeah.
present now. You can present.
Yeah. Okay. Thank you so much.
Yes, yes.
Is the screen visible and
Yeah, it's visible
yeah,
and you are audible.
audible? Yeah.
Yes,
Thank
please.
you so much. Uh, Good day, everyone. I'm Shrutia, currently working at the National Institute of Engineering and a research scholar under Dr. Shashidhara HR. So I'll be just briefing about the different the test bench, the layer test bench, and uh, and then tool that can be used online, that is an EDA playground, where I'll be showing a simulation of the constructs that we had discussed yesterday, that is system Verilog constructs, and how to use the tool, the necessary setting that need to be done. So begin with, mainly this is about the IP verification. So the major responsibility of an IP verification engineer will be lying on finding the bugs in the design, and that too with the help of the test bench components, which is built using the language, and here we have considered as system Verilog. So where exactly is the test bench? The test bench is the one who's going to give us the required stimulus, that is the input pattern, and the one who's going to obtain the responses. And it is the one who is going to check the design under the verification, or in some of the ways we can say it as design under test. Now, uh, the verification engineer here, IP verification engineer, will also be having the responsibility to find if all the RTL code that has been written is covered or not, based on the specification that is being given to the uh, engineer. So here we'll be mainly covering the code and the functional coverage. That will be majorly important. And also with that, the power and timing simulations will also be taken care of during the runtime. And we also have to observe how many functional bugs that will be popping up. And we have to also clear those bugs based on the requirements. And how are we going to check? We are going to check with the help of assertions. And once, if all these are done, we can tell that the 100% coverage is being obtained. And only then we can say that the IP verification is complete. So what are the things or the functionalities of a design through the simulation that can be done? The main purpose of a test bench. So first, we need to generate the stimulus. Along with that, we need to drive the input with the generated stimulus. Along with that, we have to provide allow the design to process the input and provide the output based on the things we have inputs that we have given. Then we have to check for its functional defects based on the output that we have received and the reference or the expected behavior. With a comparison, we can find out whether the functionality is being achieved or no. And if we have found any kind of functional bug, if it is there, then we need to fix those bugs. And after this, we have to repeat the process for many more steps until all the functionality bugs are being solved. So this is the main purpose of the test bench. So now we can achieve the 100% functionality, or we can check the functionality with the help of the layered test bench. So layered, when we say layered test bench, we feel that it's going to make the test bench more complex. But actually it is not so. It is going to make us make the tasks that are going to be followed much simpler or easier. The main reason is that we'll be going to divide a larger code into smaller pieces that can be developed separately, and then we can assemble it together for the verification. So this is how a layered test bench would mainly look like. So this major test bench, whatever we write, will be wrapping around the DOT, and here it will not only provide the stimulus, it is also going to capture the responses. So we'll go through the layering first. So initially we're going from top to bottom to up in the layering. So first in the lower layer we have signal. So in this signal layer is nothing but the device that we are going for, which will be going for the testing purpose. So this will contain all the signals that connect to the test bench mainly. Then comes the command. So in the command layer, we have driver, assertions, and monitor. So now the DUT will be driven. The DUT input will be driven by the driver. So that mainly runs on the single commands, like whether it is bus read or bus write operations. Followed by that, this output drives the monitor. The output of the DUT is going to be driven by it's going to drive the monitor here. So it will take all the signal transitions and group them together into some commands. Here we also have assertions. So assertions mainly are there to check the behavior of the design. So they are going to look at the signals individually, but it will look for the changes across the entire command, whatever is there. So it sees the signals individually, gives the changes of the entire command. Now, next layer that goes is to functional. So in the functional layer, we have agent, scoreboard, and checker. In the agent, mainly agent block can also be called as a transactor in the VMM, that is verification methodology manual. So here this is going to receive high level of transactions. Now we have to break these commands. This agent is going to break the transaction commands that are going to come from the generator into smaller commands, individual commands, and it will be giving it to the driver as well as to the scoreboard. Now what will the scoreboard do? So it will receive the commands from the agent, as we can see here, the scoreboard, and it predicts the results of the transaction. And we have the next module, that is the checker. So this checker is going to have compares the commands from the monitor with those of the scoreboards to give us the result. Now for the agent, we need the signals to be coming. So we have a generator who is going to do that. So generator is the one who is going to, it's in the scenario layer. So here what happens is this is the one who is going to give the verification component that can create valid data transactions, and it is going to send to the driver. Then the driver is then simply going to provide it to the DUT. Okay. Now we have the monitor who is going to check, who is going to display the results, and we have the scoreboard who is going to give a comparison study. So here the agent gives the result inputs here also, and when the result which comes through the DUT is going to be compared. So the direct input here, what we are going to get, we can call it as reference model. So this is the reference model, this is the real model. So if there, during the comparison check, if there is an functional defect, like the results that are reference model's result and the DUT model's results are not same, so then we can say there is a functional defect in the design. So this part is done by the scoreboard. So this generator will usually give us all possible parameters, that is the random constraint values. So we had discussed the random constraint randomization operations in yesterday's session. So all the random constraint values will be given and they will be working as the parameters, and all these data will be generated over here. So this all constitute to be the environment. Along with that, we have what is called as a test here. So all the functionality that needs to be added will be given at the test. Now, once we cannot keep modifying the entire environment for all the different test cases. So that environment has to be quite general, wherein we can add on certain features into it based on the requirements of the projects. So functionality can be added, but usually when we are designing, we can keep up some hooks such that the minor modifications that can be done will be done without affecting the entire environment. So once the testing is been done in complete, then we can go for what is called as the functional coverage. So this is the one who is going to measure the progress of all the tests and help us in fulfilling the verification plan requirements. So here, based on the functional coverage, we can change the code in order to achieve 100% coverage. So this is the layered test bench. So as per, if the design is going to be quite complicated, then the requirement would be that the test bench would be more sophisticated. So in a nutshell, the things that we have discussed here, the main objective of each block is been described over here. So there is an extra component that has been included, which is called as the interface. So the interface is not there in the previous diagram. There are various layer test bench images that we can obtain. So in this test bench, there is no interface in the layer test bench. But if the layer interface, if the interface is being included, where would that be included in the device, in the design? So usually this is going to contain design signals that can be driven or monitored. So here is what the interface is all about. So now interface comes into picture whenever you are trying to go for a very huge design where you have large number of inputs and outputs that need to be connected. So this is going to work as the one which is going to represent all the bundles of wires with intelligence such as synchronization and functional code. So the main clocking condition can be given to this interface. So it is going to be in between the test bench, and here the arbiter is mentioned, that is nothing but the device which is going for testing. So that's a DUT. So what will be the benefit of using an interface will be that this using an interface in the design will actually be suitable for design reuse, and this will also reduce the possibility of misconnecting the signals. Now This, how can we use that? It can be instantiated like any other module, and you can also connect to ports like however you connect a signal. But the drawback would be of using an interface is that if you have any kind of point-to-point connections, then the usage of interface will simply be increasing your verbose, that is your the length of coding will simply be unnecessarily increased. So usage of interface should be done suitably. And if you're trying to have more than one interface in your design, then the connecting the two different interfaces, that would be slightly difficult. So this is all about interface. Then we have what is called as the self-checking test benches. So here, so the test bench, it is created by applying some kind of inputs, sample the outputs of the DUT as you can see here, and compares the output with the expected results, and then if it gives a result on its own by the comparison, then you call it as a self-checking test bench. So this kind of test benches for all design is actually recommended, but the reason why it is recommended because it is going to provide an easy way to detect, understand, and fix the errors. The alternate approach that we usually go for is checking the results visually, and that too only highly prone errors can be identified when you go for visual checking. But if you have a self checking test bench which is already written, and if you have some kind of comments usually written when we are coding, that will actually help the engineers to involve in the project, and if any engineer is not involved also will be able to work with the project more effectively. So there are certain techniques for the test bench creation. So here, based on the functional specifications, so there are test bench in HDL, test bench in programmable language interface, waveform based, transaction based, and specification based. So test bench in HDLs, they are usually created using the standard HDL, that is using either Verilog or VHDL. So, but this technique will work very effectively or very fine for small designs. And if the test bench becomes more complex and difficult to maintain, if the design verification requirements are going to get increased. So that is one of the drawbacks as well as the advantages of test bench in HDL. So there are a test bench in programmable language interface in PLI. So here C programming language is used to write the PLI test bench. Then this can also be linked to an HDL simulator. So there are simulators you are going to convert the from one language to the language based on the requirements. This also can be used mainly where the test bench needs to simulate more complex functions, which is not possible to be written directly in HDL. Then the third one is waveform based. Now this technique will take the signal waveforms and edit according to the design requirements. But the necessary thing here is that we need a tool who is going to convert the waveform into the stimulus generated and the timing information that is being used to create the test bench. Then comes the transaction based. This technique is going to use the bus functional models and transaction level stimulus concepts. So bus functional models that usually called as BMFs. So here the test bench blocks, they are modeled using the BMFs, and these are that will be translating the transaction level stimulus into cycle accurate and pin accurate transactions at the DOT interfaces. And the last one is the specification based. In specification based technique, the test bench is created by capturing the specifications of the design, that too in an executable form. So here we can enhance the productivity actually, because the abstraction level for verification will be increased basically in the specification level rather than at the RTL level. So this is all about the techniques that that are used for test bench creation. So the verification, when it comes to verification, system verilog assertions are a majorly necessary property here, necessary form. So here the assertions, basically what are the users of them. So if you want to check the behavior of our design, we want to get some kind of messages that intimate them. So they are nothing but the assertions here. So they are going to help us in primarily validating the behavior of the design. So how are they going to do that? So they are going to do that by giving us certain messages, that is either warnings or some kind of errors which have been generated through certain sets of uh, statements. So here we are having three ways. One is immediate assertions, next is customizing the assertion action, and then we have concurrent assertions based on the requirements that based on the design requirements. So here first one we have immediate assertions. So this immediate assertions are simply going to be like our if else statements. So there will be an expression which will be performed based on the expression that will be performing. Based on the action that it takes, certain statements will be executed. So that will include if else condition. So if the expression is going to evaluate in such situations as values of x, z or 0, then we are going to interpret it as the false, and the assertion is set to fail. And if the interpretation is going to be true, then we call that the assertion is set to be passed. So it can be used in both RTL code and test bench to flag errors in the simulation. So this is the syntax, how it is going to have. So you are going to have an assertion label basically. So this is a user defined label. Then we have assert as being the keyword along with the expression. So this particular keyword is used in the system verilog, and it has been reserved, and mainly it indicates that the assertion will take place. Then comes the expression. So here we can have any valid expression that needs to be checked for the assertion purpose. Then we have, based on the expression being solved, you have the pass block code that will tell us the statements, or that can tell what has to be done if the assertion is true. Else we have the condition, some statements, that is fail block code, which tells us or which gets executed if the expression when evaluated is false. So these two, pass block code and fail block code, can be termed to be as an optional code based on the expression that it is going to get, which will be evaluated to. So if I take a simple example over here, we have as an example, we have taken always at the positive edge of the clock, assert the A and B operation, that is what happens at that point of time. So this is the clock. At every positive edge of the clock, it's going to check for the condition of A and B operations. So here A is 1, B is 1. So the result is pass. So this is going to be asserted as pass. The following statement, whatever is written for pass, will be executed. Then comes the next clock, positive edge of the clock. So if the A value is 1 and B value is 0, so the result here is actually going to be 0. So that is considered to be as fail. Similarly, at this point of time, at the next positive edge of the clock, so here the A value is 0 and B value is 1. Hence, the assertion status says is as fail. So coming to another case which says here that when the value of A is being raised to 1 again at the next positive edge of the clock and B values remains 1. So again the result is going to the value that is going to be returned is 1. So hence we are going to consider it as a pass. Hence the assertion will be of the pass statement. So this is how the assertion, the immediate assertion works. So this kind of assertion is mainly suitable, or we can tell it is intended for use it in the simulation, not suitable for much of formal verification. Then we can also customize the assertions by giving certain actions. So there are certain functions that can be used if we want to pose any kind of messages based on the actions taken. So there are 4 functions that can be used to print the message, that is info, warning, error and fatal. So these are allowed only inside the assertions and we cannot use them in the procedural code. That is the main condition. So whenever we can tell as fatal is a runtime fatal, and if there is any error is a runtime error. So warning, runtime warning based on the operation that we have taken, and info which will be asserting failure carries no specific severity. So here as an example, we are going to assert, we are going to assert the value 2 bits of 0 1, else condition, if there is an error, the error will be post, we are going to assert the error here, that will display as grant not asserted. So these are the 4 functions that can be used if we want to print any message. So this is how we will be customizing the assertion actions. Then we have what is called as concurrent assertion, Verilog assertions. So here in concurrent assertion, this usually takes place only at the clock ticking, occurrence of the clock. So uh, the behavior is going to continuously run over the time. So it is going to take place continuously. And then here the expression whatever will be there will be tied to the clock. So only with the occurrence of the clock, either based on the positive edge or negative edge, how we define it. So whenever there is occurrence of the clock, only the expression that we have written will be executed. So how would we differentiate between the concurrent assertion and immediate assertion? Because most of the construct looks similar. So the only way to differentiate is the usage of keyword property. If the property keyword exists, then it is going to be concurrent assertion. So the expression that will be written will be evaluated only at the clock edges, and then based on the variable values that will be given to it. So this is all about the assertions. Next comes, how are we going to tell the design that we have written is the verification done as covering all the conditions. So that we can tell it as by going for a coverage. So here we are going to measure the tested and untested portions of the design, and based on this, if all the possible conditions or scenarios have been checked and the results have been analyzed, then we can tell we have obtained the 100% coverage based on, and this is using the feedback loop to analyze it. So how does the functional coverage actually take place? So you are going to identify the holes. Then we are going to make the minimal code modifications. Then we are going to go it for directed test cases. Then along with that, we are going to add some constraints. So whenever we are going to add constraints, and we go for constrained random testing. Once that is be done, for the constraint random testing, you have to go for many runs based on the different seeds that we are going to give. Once all these takes place, and if there is any kind of functional cover not achieved, then we have to repeat the process by identifying the holes again, then going for the changes in the codes, making modifications and running the test cases, and then coming for the coverage again. So this is a continuous process over here. So by doing it in loop, we can achieve, we can solve many errors that can come over time, and that will account to the functional coverage. So our motto is to have 100% coverage. So we have what is called as the coverage flow. Now this the format in which the data storing coverage data will be dependent on the vendor as well as on the tools, analysis tools that we will be using. So in general, we get the design specification. Based on the design specification that has been given, we create the verification plan. And based on the verification plan, we are going to conduct the tests. Then we have, based on the design verification, we have what designs that we have done. So these constitutes to the coverage database. Now, once the coverage or database evaluates, if it is a pass, then we go for coverage analysis, then the repetition of the process. And if there is a failure and if there is any kind of error that takes place, then the result would be of a no. So then we have to go back to debug the design based on the design specification that has been given to us. So what will be the following, what will be the actions that will be taken with those tools who are going to go with this analysis? First, basically they will run a test with multiple seeds that will be given. Once the data is be given, it will check for its condition on pass or fail. And based on this, we can have the functional coverage information, and this validation or the information on the coverage will be stored only if the simulation is successful. And then after that, all the successful results will be stored, and we are going to analyze this coverage for many runs. So this is the actual flow in which the steps that takes place whenever you are going for using the tools for coverage. So there are types of coverages that are there. So basically we have mainly two types of coverage, that is usually the code coverage and functional coverage. So along with that, we have two more, that is the bug rate and assertion coverage that are uniquely defined. So when we talk about code coverage, so we have the design specification given. So for the design specification given, we are going to have a program written to it, the code written to it. So we are going to measure the design implementation now. how the given design has been implemented, and we are taking certain parameters consideration for it. First one is that how many lines of code that will be executed. Based on the lines that we have written, how many of them have been covered, or if there are any kind of lines of codes that are redundantly written. Second, we are going to see the code and the expressions have been executed, that is all the paths, possible paths that we have written for based on the specification, will all the paths be covered through the code. Next comes the toggle coverage, which will tell us the based on the bit values, which single bit variables have had the values of zeros and ones. And the third one and the fourth one, which will tell us about the FSM coverage, like if we have written any kind of a state diagram, then the transition should take place from one state to the other state. So here we have to see how many state transitions have been taken place, or how many state machines have it been visited. So this, in the given state machine, how many states it has been visited. So that will give us the FSM coverage. So the code coverage covers these four main aspects based on the design or the implementation that we have done for the design specification given. This also tells us about the tool, because how are these being evaluated based on the tools that we are going to use. So the tool is going to automatically analyze the source code, and it will help us identify if any of these code are hidden, or any of the statistics that is been missed out by us. Then based on this, at the end we can get the measure of how much the test exercises the design code. And finally, the code coverage will help us to know how thoroughly the tests have been implemented based on the design specification given. And here we are not actually covering the verification plan. We are only looking into the design aspects. Are all the design conditions being met? So that is the motto of the code coverage. Then we have the functional coverage. So the functional coverage, actually we can also call it as the specification coverage. And in this functional coverage, we will actually get to know some of the errors that will not be detected by the code coverage. For example, we might have written a certain set of codes, and those block of code which would be necessary for design, but we might have not written it down. So we might have missed that kind of an operation. But when we go for functional coverage, such kind of operations or such kind of block of things that we have missed out can also be detected. So code coverage may not help us identifying the block of codes that have been missed out based on the design. But when we go for functional coverage, which we are going mainly into looking the specification coverage, will help us identify such kind of bugs also, so that the verification, so the coverage will be complete to the 100%. Along with that also comes into picture is the bug rate. So what exactly indicates the bug rate? So initially when we write the program, or when we write the test bench, and when we give the when we put the device for testing, the bug rate initially will increase. So these bug rates are measured with time based on the number of weeks we have been working in the project. So excuse me. So initial bug rate should be actually very high, and with uh, time the bug rate should taper down to 0. But actually the bug rate usually don't taper down to 0. because there will be changes that can take place at as per the time based on the verification that will be done by various people. So the aim would be that with time the bug rate should go to 0 or to the minimum as in practical scenarios. And the last one is the assertion coverage. So we know how what assertion is. So the assertion coverage should help us to identify for all the conditions that we have written. The assertion should give an result by telling whether the operation that has been taken place is a successful one or an not a successful one. That means if any of the grants have been requested, it is a assertion coverage that has to indicate that all the grants have been accessed. If any of them is been missed out, then that also has to be intimated. The next important function of the assertion coverage would be that most of the operation that we need should be mutually exclusive. So if there aren't any mutually exclusive events that have been taken place inside the code, then such kind of ambiguities should also be intimated, and that will be taken care of by the assertions. So that indicates the assertion coverage. So when we cover all these four aspects, that will complete the cycle of the coverage, that will help us to complete the verification 100%. So there are some strategies that have been followed to obtain the coverage into 100%. So first one is the main intimation is that we have to gather the information and not the data. So information here is that based on the stimuli that we give, what is the result that is being obtained. So that is what is to be gathered, and not the data that have been given into it that has to be collected. So that will be the first strategy. Second strategy would be that if we have to measure only what we are going to use. So there are certain times that we may not know the parameters that we are going to give. So during the due course of time, to obtain 100% completeness, we might have to measure various results. So but keeping this all the results may not be an useful one. So that will cover to that we have to keep only what is necessary, then discard whatever is not. So we are going to measure only the ones which we are going to use. And the last one is that how do we measure the completeness? So to measure the completeness, we have a chart over here which says the functional code versus the functional coverage versus the code coverage. So usually at the initial step, we have the functional coverage as well as the code coverage being low. So this is during the starting of the project. So this will help us to identify what are the tests that we are giving, which are the inputs that are necessary, which are not necessary, and the seeds that which we have given are actually needed or not needed. So this will help us to identify that the parameters or the C's that are necessary for further testing. So this usually happens at the initial stage of the project. So where your code as well as the functional coverage is low. Then as we proceed, the scenario will come where we have a very high code coverage, but the functional coverage, very low code coverage, but the functional coverage is high. So at that situation, what happens is there are chances that some of the cases that had to be tested would be left out. So at that point of time, we will need more and more points such that the functional coverage will be achieved. So here we will need to think of in the verification part, like which are the points that have been missed out. The next comes the, if we have a very good code coverage, and functional coverage and a very low functional coverage. So what at this point of time, what happens is, you might feel that you have covered all the design aspects, but some of the functionality tests may not be done over here. So at that time, we might need to use some kind of tool which will help us to identify and help us to get the good functional coverage. So the design part would be complete when we have an high code coverage, but the functional coverage, we need some tools that will help us to identify and put them together. Then the last one is having a good code coverage, that is high code coverage as well as high functional coverage. That means you have going to, that is the ultimate thing that we need. But what matters here is the bug rate. So according to us, the bug rate should actually decrease over the course of time. But then it is like we are, the good designers are not very well satisfied. That means you have to look into even more scenarios or possibilities then other than what is being done to obtain even uh, more functional coverage, such that the bug rate actually decreases with due course of time. So here different approaches, there is a need to look into for different approaches, like we have to have new combinations of the design blocks or inputs such that we create more error here. So error generators are required. So if that is done with the decrease of the bug rate over the due course of time, then we can tell that there is a good coverage. So this is all about the strategies that are being used for functional coverage. So with all these info theory base now, we will just go to use the online tool that is available, that is the EDA Playground. I'll just share the screen there. Okay. Is the screen visible of the EDA Playground?
Ma'am, it's visible.
Okay. So for initial verification of the design, so we can have online tool, that is the EDA Playground. Now here, this EDA Playground, it's easy to use, and you just have to register into it by giving the username usually being the email ID through which we are registering. And this is going to save all your work. And moreover, here what happens is that if anyone else is also working on the similar kind of a project, if you publish it, you can the others will also be able to edit your code or work over it. Here what happens is, there are two parts which has, first part here you are going to write the code, and in the second part you are going to write the test bench for testing your this is the device and this is for your testing purpose. So here we have to have some selections that has to be done based on the language and the libraries that you are going to use. So here the options that are available if you want to use the EDA Playground is using System Verilog or Verilog. That is what I've selected here. Along with that, you can try with VHDL, Python, C++, Perl, and CSH. If you want to have verification done, if you know the verification language, then we can go and select one of these options. There are other libraries, if you wish to include, can be selected over here. And then if you want to enable any other testing that is based on the design, can also be selected over here. Based on the selection that we do, that is for your language, test bench and design, there are tools that are available. So there are some commercial simulators and there are some free simulators. When we come to System Verilog, not all support the System Verilog. So I have selected Mentor Questa 2001.3 version here. So this one is helping me to simulate the System Verilog very effectively. Not all support System Verilog as effective. When it comes to iCaris, these ones are mainly useful for Verilog operations. So here are mainly for Verilog. Then we can select the time scale for simulation as per the requirement. And to run, if you want to have the waveform being displayed, then we will have to open the EP wave, that is open EP wave after run. So this is the one who is going to help us get the simulated waveform being displayed. And also if you want to download any of the file, then we can go for download files after run over here. So there are certain examples based on the program, kind of program that we need to learn. So there are examples available here. So I have taken the program of dynamic arrays to run. A dynamic array is a construct that is purely non-synthesizable. Hence, only the simulation part will help us to obtain it. So here, what I've done is that taken a simple counter program, but written using the dynamic array format. So I've written two programs. One is using the fixed array, and the other one is using the dynamic array. So while using the fixed array here, some of the things I have commented it due to some reasons. I'll tell it later on. So when we go for fixed count, that is the usual way in which we write the program. The only change that I have taken, that has been taken place here, is that you're using the data type called as logic, whereas in Verilog we would not require it. We would declare the output as reg based on the kind of modeling that we are going to do, whether it is behavioral or data flow, or whether it is in a structural level. So here we are going to, I have taken the behavioral model, and since all the data has to be remembered, then we have to go for a reg kind of an data type. But here there is an option of using logic. So irrespective of whether it is a wire or whether it is an reg. So we have taken clock reset as the input, and 3 down to 0 C out. That is, we have taken it to be counting it from 0 to 15. So 4 bits. So this is the regular clock, regular counter program. So since the date, this has been defined, the range has been defined, we are going to call it as the fixed count or the fixed array. When it comes to dynamic array, so how are we going to write it is, so I have declared an intermediate memory that is called as dynamic dyn, and I have not specified what is the array size here that has to be allotted. But I have given the number of bits that each element should have, and that is 4 bits. And I have declared it as of the type logic. So the data type do matters when we are going to use any kind of the dynamic kind of arrays, that is whether it is dynamic array queues or whether it is associative. The data types do matter there. So initially I'm going to allot, I just want to allot the memory location, allocate the location for the array only once. So going with an initial block, and the new is a keyword which is going to tell us how many locations I need to allocate it for. So I'm just taking one. I just need one location, and that location needs to have 4 bits. Needs to store 4 bits, and then initializing that the 0th value to be as a 0. I mean, I'm just initializing it, and then with the every positive edge of the clock, the operation begins. So initially, if the reset is set to 0, if not of reset, I'm making the dynamic array value, the element value to be 0. Else, it has to add. So this add will take place here, and then the value whatever is being obtained is put to the actual output, that is C. So this is an intermediate array here value. So whatever is been the counter, whatever it's been counted will be put to C here. This is all of the design. Coming to the test bench. So here given the name as a test bench. Here we are going to declare the stimulus, that is the clock and reset, and the output response being the C as per here. Now I am going to have the named association format over here. So the device that is going for testing is count, as my module name is count over here. So this is C out, and this is the name of the instance that has to that is given, and I'm just going to map the signals of the test bench to that of the device. So here it is clock with the clock, reset with the reset, and C to the C. Then I'm going to have, I need a clock to because my entire things works with the positive edge of the clock. So here, as for every delay of 5 units, so the clock wave is been changing from positive to negative. So the clocking takes place over here. So at the beginning, initially, my clock as well as the reset values are going to be 0, and that too for after 20 units of delay, I'm going to change the reset value to be of 1, and that is going to retain for another 150 units. And after 150 units, I'm going to change the value of reset to be 0. And then after units of 20, that is 20 delay units, I'm going to set the reset value to be 1. So then after the value of 200, once the 200 is obtained delay, so I am trying to finish the simulation there. So this is a time duration for which my entire simulation is going to work for. Then here there are in exclusive commands which is called as a dump file and dump vares. Now, since the values has to be displayed through a waveform, that means all the changes that are taking place has to be stored in a file, and that file is nothing but the .vcd file. So the wave editor that is there here, EP wave, not only that, if you are going to have a GTK wave also, then you will need a file that those editors will need a file that it will read for the changes of the inputs that takes place, and that is stored with a .vcd, that is value change dump. So you are going to dump the file that is taking place here into this file. So dump is just the name of the file that has been given with the extension of .vcd, that is value change dump. Now all these changes, if it is taking place, it needs the variables, okay, for its changes. So either you can declare with the syntax by specifying the values of the test bench, the type and all, or else by simply writing dump vares. So dump the variables, and all the when you dump the variables, all the changes that takes place. So if you write this dump variables, it will include everything, all the variables that are which are being used inside the used for testing will all be called. So dump these variables, and all the changes based on the variables that are given that will be taken place will be stored in the .vcd file. So this .vcd file will be actually read by the wave EP wave. So all the changes that will be done can be saved, and we can just click on run, and this waveform will open. So if there is any kind of error, or if there is any kind of warning that takes place, will be the log. So we'll get the detailed log of this operation that is done. So all the errors will be mentioned over here. So this is the waveform that we are going to obtain based on the inputs that we have given. It's just printing it twice. There's nothing change in the operation. It's just displaying it twice. So this is the output that we are going to obtain based on the simulation timing of the reset. So if after 20 units delayed, we have made the reset value to be 1. So during that course of time, we can see that the counting takes place at the output. So values from 1 to F have been read, including the 0. So 0 to F will be counted, and due course of time after 150 units, after delay of 20, or we have to made the reset value to be 0 for 20 units, and again high. So this is being present over here. So the duration simulation value we have given, but it is taking the maximum it can fit in. So only so much will be the displayed value. So this is how the counting takes place. So it's a simple up counter, but by using the system Verilog dynamic array construct. So that is how, and this is how we can use the EDA playground for operations. Now, if we want to change the stimulus of the main module to that of the test bench, then that can also be done, since I have taken here as C out here, and I have mentioned here it as out in the test bench. So how are we going to map it? They have been mapped it using the reference here. So C out is with respect to the module, and this is the out is the one with respect to the test bench. So the names of the stimulus at the test bench as well as at the DUT need not be same, but it only purely depends on the way we are going to link it. So if the mapping is done, and again if the order is positioning also matters, is done exactly, then that will help us get the result. So this also will give us the counting. Now the only change is that if I use another kind of another layer of memory element over here just to store the values, then what happens is the result is going to get delayed by one clock cycle incomplete. So if I run this particular code, so this is going to give me the same result as priorly, but if I change and put an intermediate value here, it is be noticeable here. So the actually the CC is an intermediate register which is going to keep the count and then pushing it to the C out. So we can clearly observe that the intermediate register takes the value at the right time as per the changes, but when it is moving out to the clock to the output register, it is taking one clock delay. So this is with respect, this output here is with respect to the test bench, and this C out is with respect to the DUT, device under the test. So we compare this with the register that we have used intermediately to do the operation and storage. So we have a delay of one clock cycle. So this is one of the observation that can be seen if we are going to use intermediate registers if not needed.
Audience, if you have any questions, please ask. You may type the questions in the chat box.
Sorry. So this here we come to the end. So if you have any questions.
No questions. I have not seen any questions in the chat box. Shruti, it's done for today.
Yeah, there's one question. What's the meaning of gather information, not data? Here, as per the for functional strategy, it says that rather than having the data that we have fed in. So what happens once the data is been fed, that information that we receive. So that will be mainly important for functional coverage. What is the results that have been obtained when the result when the intended in seeds are given? So that is the meaning of gathering the information.
Yeah, Shruti, I have one question.
Yes, ma'am.
Actually, when we are going to design or verify using our conventional tools like Vivado, etc., can we do the same thing using EDA Playground, or it is having some limitations?
What kind of operations, ma'am?
Like hierarchically, if let's say I have n number of files, I am calling those files hierarchically in a bigger design. So can I do the same thing in EDA Playground also?
Yeah, there is some limitations. Uh, in EDA Playground, what all you are doing, it's only for a simulation modeling. It can't be synthesizable. Some of the constructs cannot be synthesizable. Once you go to the Vivado tool, so the synthesizable construct should be done. If you are targeting only for an ISC simulator in a Vivado, so then the EDA tool constructs will be maps directly to the ISC simulator. But if you're thinking for an synthesis and implementation process, the some of the code, some of the constructs should be remodified with respect to that.
But if you're looking for hierarchy like that, you can have multiple. That is allowed in EDA Playground.
Okay, thank you so much. Dear participants, if you have any more questions, you please feel free to ask. You may type in the chat box. Our speakers are here to attend the questions. So I think they don't have any questions.
Oh, well done. Let me see your. Thank you, Menka. So like, do we have any simulation tools, which can, which can install, and, we can do verification and all, professors, Professor and Shruti?
Sir, we can go with model sim, that is for functional verification, or Questa sim for functional verification.
No, these are all, no, I'm sorry. My question is open source based tools.
Open source based
Oh,
tools. I didn't try it actually. We are using only the Questa sim and Cadence NC simulator for
oh,
all.
these are all very expensive tools, right? Actually,
Yeah.
but there is a open source
For
momentum.
particularly for NOC verification, there is so many open source. So we are using NoxSim for particularly for NOC simulator. So that is using System C. We are doing it. Some of the System Varilla construct also we can borrow it, and we can do it with the NoxSim also.
Oh, which one it is?
NoxSim.
Yeah, spell it.
NOXIM. Is it right, Kriti? NoxSim, right?
Yes, sir. It's Noxim.
Yeah, it's an open source tool. Yeah, welcome,
Yeah.
Noxim. Oh,
Yeah.
this is a University of Catania.
Catania.
Yeah,
Yes,
they
sir.
developed it. So, what are the things one
Yeah.
can do with this Noxim? Oh, very good, actually. This is what, like, we need to really, work on this. Even Noxim simulator, Google is encouraging everyone to use it. Noxim is a NOC simulator. Yeah.
Sir, it's basically for this network on chip simulation. Like if you want to know how the routing algorithms that are used for simulations, or the if you want to see how the data rate based on the data rates based on different traffics, if you want to analyze the network, then Noxim will help us to do that. The only prerequisite for Noxim will be that we need to have the proper idea on the architecture, the basic level of architecture of NOC. That's the only prerequisite required.
Oh, okay.
Uh,
So this runs on both Windows and Mac, looks like, and also, like, you could.
Windows is not that successful. The installation was not very effective. For Linux, yes, it's good. Up to
Oh, okay.
256 cores, we can go easily.
Maybe, as an assignment or something, we should develop some application, and using NOC, how to walk through this tool, that will be very useful for the students, and whatever, the open power initiative what we are making, as a open source based things, that would be very nice add on.
Yeah, Ganeshan, that's right. And we have also explored one wireless NOC tool, no? What is that, Shruti?
So, sir, this one Noxim only provides wireless NOC. That's the only tool that is.
Another open source tools we are explored, no?
Other, sir, it's Booksim and this one only, sir, Gem5.
Gem5, you guys have skills in Gem5?
Yeah, we just
We are
tried it.
exploring, sir. We are.
Actually, right, we are, yesterday there was a Gem5 talk from, not yesterday, day before yesterday, from Luke Layton, and Gem5 is a simulator for even Power ISA. So,
Yes, sir. Yes,
so
sir.
we are working on that too. Probably we can talk offline on that. And I'm actually trying to set up, the Gem5 infrastructure in the University of Oregon, so that people can use that.
Yeah, that's
Yes,
nice.
sir.
So
That's
like
a
that,
very good
maybe
tool.
we'll have to list down, all these, the open source based tools, and try to form a, a kind of a consortium. I mean, a kind of, add on, to the consortium, whatever we have.
Yeah, that's right. That's right, Ganeshan.
Sir.
So we can, we are
That's good.
2 to 3 months we can explore it more, and we can come out with the knowledge of on the Booksim and Gem5 also.
Yes.
Yeah.
Yeah.
Very good. Awesome. Okay. Team, any other questions here? The Noxim simulator, we all can use it as part of, the NOC, um, you know, NOC, and support several architecture alternatives, including pipeline and non-pipeline routers. Very good. Okay. And yeah, any other questions? Menka, back to you. You can take it on.
Thank you, sir. So I can't see any questions so far. Yeah. So yes, thank you very much, Professor Shashidhar and Miss Shruti Ravi. Thank you for a nice presentation, and thank you, sir, for the nice presentation. And we'll be sharing the PPT later on through the Canvas learning modules we are going to share. So over to you, Professor Samula. It's over to you, sir.
Yeah, thank you, Menka. Yeah, thanks a lot, Professor Shashidhar. It's a long session and I very sincerely engaged. And thanks to Ms. Shruti also. I would just request if you have some set of questions to include our quiz, please share with us.
Yeah, sir. Sure. I will share by tomorrow evening. Yeah,
Sure.
I will share by tomorrow evening.
Okay.
Yeah.
Yeah, thank you very much for being here.
Can we take the quiz tomorrow or shall we schedule it on Monday?
Yeah, Mr. Ganeshan, tomorrow we have schedule, na?
Oh yeah, tomorrow we have a schedule, sir. That is how we have to do it, because you know, in between there is an holiday coming, you know, Ganesha Chaturthi, and that we didn't schedule it.
Okay, okay.
Yeah, tomorrow we
No,
have two
tomorrow,
speakers. One is actually Dr. Manikandan, who has got very good experience, and you know, even I think he has got a lot of good experience. You know, who is going to be sharing some of the stuff,
yeah,
and also Varun. Both
nice.
are industry people. So
Yeah,
yeah, that's going to be very good with some demos and all the stuff.
right. So tomorrow, participants, we have tomorrow session. And after the session, we'll open the quiz. So you should all take this quiz for assessment, which will help us in actually evaluating you for certificates. But more than that, there is a knowledge gain here. And so we should be listening to all speakers very diligently so that we have a capacity generation in the long run. So thank you, Mr. Ganeshan. Thank you, Menka. Thank you, Ms. Gayatri. Thank you very much. So all the participants, please wait for the quiz tomorrow. Till then, you can take a practice quiz as Canvas. Those who have not joined Canvas, please join it. Yeah. Thank you very much.
Thank you, sir. Thank you, everyone.
Thank you. Thank you all. Thank you. Bye.